Welcome to the calmest corner of the internet. Find a cozy spot, lean back, and let your body relax. This is more than a tutorial. It's a gentle journey through the HCL programming language. Breathe slowly. Let the words flow over you like a soft breeze. As we explore code together, may your mind ease into a peaceful rhythm. Don't forget to like and subscribe for more relaxing coding adventures. Let the learning begin. HCL, or HashiCorp Configuration Language, is a declarative language designed specifically for infrastructure as code. This means that instead of focusing on the steps to achieve a result, HCL allows you to define the desired state of your infrastructure. It is widely used to create and manage cloud resources, configurations, and workflows across various platforms. Developed by HashiCorp, HCL is deeply integrated with tools like Terraform, which is essential for provisioning infrastructure, and Vault, which handles secrets management. Its design emphasizes simplicity, making it easy to read and write, while ensuring structured data representation that aligns with modern cloud-native practices. This language is a cornerstone for teams looking to automate and manage their cloud environments efficiently. One of the standout features of HCL is its declarative syntax, which allows you to specify what you want your infrastructure to look like without detailing the steps to achieve it. This approach enhances clarity and reduces complexity. The language is intentionally designed to be human-readable, with a straightforward structure that makes it accessible even to those new to infrastructure automation. HCL supports variables, functions, and modules, which enable you to break down complex configurations into manageable, reusable components. Its cross-platform compatibility ensures it works seamlessly with major cloud providers such as AWS, Azure, and Google Cloud. Additionally, HCL integrates tightly with HashiCorp tools, creating a cohesive ecosystem for managing infrastructure, security, and automation across different environments. HCL is particularly powerful in infrastructure provisioning, where it can define resources like virtual machines, storage, and networks across cloud platforms. It is also used for configuration management, ensuring consistent settings for cloud environments, such as network policies or user permissions. Automation of deployment pipelines is another key use case, where HCL scripts can trigger resource creation or updates based on specific events. It is also instrumental in defining policies and security rules, such as access controls or compliance checks. Finally, HCL allows the creation of reusable templates, which act as blueprints for deploying resources, saving time and reducing errors in repetitive tasks. These capabilities make HCL a versatile tool for modern cloud operations. This course aims to equip you with a solid understanding of HCL fundamentals, starting with its syntax and core concepts. You will learn how to write and structure configurations effectively, which is essential for building scalable infrastructure. We will explore variables, data types, and control structures, which are critical for dynamic and flexible configurations. A significant focus will be on creating reusable modules and functions, which are key to organizing large-scale projects. Finally, you will apply your knowledge to real-world scenarios, such as provisioning cloud resources or automating workflows to gain hands-on experience. By the end of this course, you will be well prepared to leverage HCL in your own infrastructure projects. The syntax of HCL is built around blocks, which are used to define resources and their properties. For example, a block might look like resource instance example, where the first part is the resource type and the second is a unique identifier. Within these blocks, attributes are defined as key value pairs, such as AMI equals AMI 12,345, which specify the characteristics of the resource. Comments are a useful feature, starting with a hash symbol or double forward slashes to explain parts of the configuration. While indentation is not required, it is strongly recommended to improve readability, especially for nested blocks. Nested blocks allow for complex configurations, such as defining multiple properties for a single resource, making HCL both flexible and easy to manage. HCL supports a range of data types, starting with primitive types like strings, numbers, and booleans. These are the building blocks for any configuration. Collection types, such as lists, maps, and tuples, allow you to group related data, making it easier to manage complex structures. Dynamic types are another key feature, where the type of a value can change based on context, offering flexibility in configurations. HCL also includes functions like toString and toNumber to convert between types, which is useful when working with variables. Additionally, null and undefined values values are used to represent optional fields, providing a way to handle missing or conditional data gracefully. These data types make HCL adaptable to a wide range of use cases. Control structures in HCL provide the ability to add logic and dynamic behavior to configurations. The if statement allows you to conditionally include or exclude parts of the configuration based on specific criteria. For loops, such as for and count, enable the creation of multiple instances of a resource, which is essential for scaling. The for each function is particularly powerful for iterating over collections, allowing you to generate resources dynamically. While loops are less common, they can be used for more complex iteration scenarios. Finally, try and catch blocks help handle errors gracefully, ensuring that configurations do not fail unexpectedly. These structures make HCL a robust language for managing complex infrastructure scenarios. HCL includes built-in functions for tasks like string manipulation, mathematical operations, and data processing, which are essential for transforming and using variables effectively. User-defined functions allow you to encapsulate custom logic, making your configurations more modular and reusable. Modules are a core concept in HCL, enabling you to organize configurations into reusable components that can be shared across projects. These modules use input and output variables to interact with other parts of the configuration, promoting a clean separation of concerns. Terraform modules, in particular, are widely used to create reusable infrastructure components, such as virtual private clouds or databases, which can be deployed across different environments. This modularity is key to building scalable and maintainable infrastructure. In summary, HCL simplifies infrastructure management by providing a declarative, readable, and structured approach to defining cloud resources. Mastering HCL allows you to automate complex workflows and manage infrastructure efficiently, which is critical in modern cloud environments. The next session will dive deeper into advanced HCL concepts, such as nested modules and complex data structures, to further enhance your skills. Practicing by writing HCL configurations for real-world scenarios will solidify your understanding and help you apply these concepts effectively. I encourage you to explore the HashiCorp documentation and community resources to continue learning and stay updated on best practices. This foundation will empower you to leverage HCL in your own projects and contribute to more efficient cloud operations. A well-structured development environment is essential for effective HCL programming. It ensures that you can write, test, and debug your code seamlessly without interruptions. Imagine trying to build a house without the right tools. Your work would be slow, error-prone, and inefficient. Similarly, a robust development environment provides critical tools like syntax checkers, which help catch errors as you type, and compilers that translate your code into executable programs. It also allows for execution, so you can see the results of your work in real time. Beyond functionality, a standardized setup ensures that every team member works in the same environment, which is crucial for collaboration. This uniformity reduces compatibility issues and makes it easier to share and review code across the team. Before setting up your HCL environment, you need to ensure your system meets the necessary requirements. First, install a compatible operating system such as Windows, Linux, or Mac OS. Each of these platforms has its own nuances, so it's important to choose the one that aligns with your workflow or team standards. Next, check that your system has sufficient resources. At a minimum, 8 gigabytes of RAM and 20 gigabytes of free storage are recommended, though more may be needed for complex projects. Processing power is also a factor. Ensure your CPU can handle the demands of compiling and running HCL programs. Finally, download the latest version of the HCL compiler and any required libraries. These tools are the building blocks of your development process, so using outdated versions can lead to unexpected issues. Always verify the integrity of your downloads to avoid security risks. To begin, visit the official HCL website to download the installer for your operating system. This ensures you get a reliable and up-to-date version of the compiler. Once the installer is ready, follow the step-by-step instructions provided by the installation wizard. These steps may vary slightly depending on your OS, but they typically involve selecting the installation directory and agreeing to the license terms. After installation, it's crucial to verify that everything worked correctly. Open a command prompt or terminal and type HCL version. If the installation was successful, this command will display the version number of the compiler, confirming it is properly installed and accessible. If not, you may need to troubleshoot the installation process or check for system compatibility issues. Configuring environment variables is a critical step in making the HCL compiler accessible from anywhere on your system. Start by adding the compiler's installation path to the system's path variable. This allows you to run HCL commands from any directory without specifying the full path. Additionally, set environment-specific variables such as HCLHOME, which points to the compiler's root directory. These variables help the system locate necessary files and configurations. Once the variables are set, test the configuration by running a simple script. For example, create a file with a basic HCL program and attempt to compile and execute it. If the script runs without errors, your environment variables are correctly configured. If not, revisit the setup to ensure all paths and variables are accurately defined. Choosing the right integrated development environment, IDE, can significantly enhance your productivity. Popular options like Eclipse or Visual Studio Code offer a range of features tailored to programming. For HCL, install plugins or extensions that provide syntax highlighting, code completion, and error detection. These tools make it easier to read and write code, reducing the chances of typos and logical errors. Once the plugins are installed, configure the IDE to use the HCL compiler you previously installed. This involves specifying the compiler's location and ensuring the IDE recognizes its capabilities. A properly configured IDE becomes your central hub for writing, testing, and debugging HCL programs, streamlining your workflow and improving efficiency. In addition to the compiler and IDE, a few essential tools and dependencies are necessary for a complete HCL development setup. A reliable text editor like Visual Studio Code or Notepad++ is invaluable for writing and editing code. These editors often integrate with other tools, making them versatile choices. Version control systems like Git are also crucial, especially for collaborative projects. They allow you to track changes, revert to previous versions, and manage code across teams. Finally, install debugging tools and any required libraries that your projects may depend on. Debugging tools help identify and fix issues in your code, while libraries provide pre-written functions to simplify development. Together, these tools form the backbone of a functional and efficient HCL development environment. Testing your setup is the final step in ensuring everything works as expected. Start by writing a simple "Hello, World" program in HCL. This classic example is a great way to verify that the compiler and runtime environment are functioning correctly. Once the code is written, compile it using the HCL compiler. If there are no errors, run the program to see the output. A successful run confirms that your environment is properly configured. However, if errors occur, carefully review the messages provided by the compiler. They often point to specific issues, such as missing dependencies or incorrect configurations. Resolving these problems ensures your environment is ready for more complex projects and prevents potential roadblocks down the line. Despite careful setup, issues can still arise. One common problem is missing environment variables, which can cause the compiler to fail when it cannot locate necessary files. For example, if the HCL variable is not set, the system might not recognize the compiler's location. Another issue is conflicting versions of HCL or dependencies. If multiple versions of the compiler are installed, the system might use the wrong one, leading to compatibility issues. Incompatible IDE configurations are also a frequent culprit. If the IDE is not properly linked to the HCL compiler, it may not recognize the language or provide accurate syntax checks. These problems can be frustrating, but identifying them early helps maintain a stable development environment. When faced with setup issues, the first step is to consult the HCL documentation. It often contains detailed explanations of error messages and solutions to common problems. If the documentation does not resolve your issue, seek help from online forums or community support channels. These platforms are filled with experienced developers who may have encountered similar challenges. If all else fails, consider reinstalling or updating the affected tools. Sometimes, a fresh installation can resolve lingering issues. Additionally, check for updates to the HCL compiler, IDE plugins, or dependencies, as newer versions may address known bugs or improve compatibility. Persistence and systematic troubleshooting are key to overcoming these obstacles. A properly configured development environment is the foundation of successful HCL programming. It enables you to write, test, and debug code efficiently while ensuring consistency across teams. By following following the steps outlined in this presentation, installing the compiler, configuring environment variables, setting up an IDE, and testing your setup, you create a reliable foundation for your projects. Addressing issues promptly is equally important, as even small problems can escalate into major roadblocks. Remember, a well-maintained environment not only improves productivity, but also enhances the overall coding experience. With these practices in place, you'll be well equipped to tackle any HCL project with confidence. HCL stands for HashiCorp Configuration Language, and it is specifically designed to create declarative configurations that are easy to read and maintain. This language prioritizes simplicity and clarity, making it ideal for defining infrastructure in a way that is both intuitive and structured. The core elements of HCL include blocks, which organize configurations into logical units, attributes that define specific settings within those blocks, and expressions that allow for dynamic values and computations. These components work together to enable users to describe their infrastructure in a way that is both human readable and machine executable. HCL is most commonly used in infrastructure as code scenarios, where it helps automate and manage cloud resources efficiently. The basic structure of HCL revolves around three key elements: blocks, attributes, and expressions. Blocks serve as containers for related configurations, such as defining resources, modules, or other configurations. For example, a block might look like resource instance web, where the block type is resource, the identifier is instance, and the name is web. Attributes are key value pairs that specify details within a block, such as AMI equals AMI 123,456, which sets the Amazon machine image for an instance. Expressions allow for more complex logic, such as using count equals 2 to create multiple instances, or defining provider configurations with dynamic values like region, US East 1. These elements combine to create flexible and scalable configurations. Variables in HCL are declared using the variable keyword, followed by a name and a block that defines its properties. For instance, variable region type equals string default equals US West 2 creates a variable named region with a default value. HCL supports a variety of data types, including strings, numbers, booleans, lists, maps, and tuples, which provide the flexibility needed to handle different configuration scenarios. For example, a list might store multiple instance types, while a map could associate specific parameters with different environments. By using variables, users can make their configurations more reusable and easier to manage, reducing the risk of errors from hard-coded values. Control structures in HCL allow for dynamic and conditional logic within configurations. Conditionals, such as if and else, enable configurations to adapt based on input values, like if var enable logging, to include logging settings only when a variable is true. Loops, using for expressions, can generate lists or maps dynamically, such as for I in 1, 2, 3 equals item $i, to create multiple items with incremental names. Nested blocks combine these structures with resource definitions, allowing complex logic to be embedded directly into configurations. This capability makes HCL powerful for scenarios where configurations need to vary based on specific conditions or inputs. HCL includes built-in functions that enhance its expressive power, such as format, join, and lookup. For example, format user %s. var name dynamically constructs a username based on a variable. Expressions can be wrapped in parentheses to handle complex logic, like count equals length var. Instances, to determine the number of instances based on a list. Interpolation, using, allows values to be embedded directly into strings, such as name equals server $randomid serverid, to generate unique server names. These features enable configurations to be more dynamic and adaptable, reducing redundancy and improving maintainability. Comments in HCL are essential for documenting configurations and improving readability. Single-line comments start with a hash symbol, like this is a comment, while multi-line comments use proper formatting, such as indenting blocks, ensures configurations remain organized and easy to navigate. Best practices include avoiding hard-coded values by using variables and locals, which centralize configuration details. For example, locals can store frequently used expressions, making them reusable across the configuration. Keeping blocks modular and well documented ensures that configurations are easier to understand, update, and collaborate on, especially in team environments. In summary, HCL syntax is designed to prioritize clarity and declarative structures, making it an effective tool for infrastructure as code. Mastering variables, blocks, and expressions is crucial for creating flexible and maintainable configurations. As we move forward, the next session will explore advanced HCL features and real-world use cases, building on the foundational concepts covered here. This will include deeper insights into complex configurations, best practices for large-scale deployments, and strategies for integrating HCL with other tools and workflows. HCL stands for HashiCorp Configuration Language, and it is widely used for defining infrastructure as code. Blocks and attributes are fundamental components of HCL that help structure configurations in a clear and organized way. Blocks act as containers for related settings, allowing you to group similar elements together. For example, when you're setting up a cloud resource, a block can hold all the necessary details about that resource. Attributes, on the other hand, are the specific values or properties within a block. They are key value pairs that define how a block behaves. Think of blocks as the framework of a building, and attributes as the specific materials or features used within that framework. The structure of HCL is crucial because it ensures that configurations are easy to read, maintain, and scale. A well-structured HCL file can prevent errors and make collaboration among teams more efficient. By understanding how blocks and attributes work, you can create configurations that are both functional and easy to manage. In HCL, blocks are the primary way to define resources, modules, or data sources. A block starts with a block type followed by a label, and then a set of curly braces that enclose its contents. For instance, the block type resource might be used to create an Oz EC2 instance, while data could retrieve information about an existing resource. The syntax for a block is straightforward. Block type label. The label helps identify the block's purpose, making it easier to reference later. Blocks can also contain other blocks, which allows for nested configurations. This nesting is particularly useful when dealing with complex systems, such as when a module includes multiple resources, or when a data source depends on another resource. Common block types include resource, data, module, and provider. Each of these serves a distinct role in the configuration process, enabling you to build modular and reusable code. Understanding how to use blocks effectively is essential for creating scalable and maintainable HCL files. Attributes are the individual settings within a block that define specific characteristics or behaviors. They are written as key value pairs, where the key is the name of the attribute and the value is the data associated with it. For example, an attribute might specify the type of instance to use for a cloud resource or the region where a service should be deployed. The syntax for an attribute is simple. Attribute name equals value, or attribute name equals 123. These values can be strings, numbers, booleans, or even more complex data types. Attributes are vital because they provide the detailed information needed to configure a block properly. Without attributes, blocks would lack the specificity required to perform their intended functions. For instance, in an EC2 instance block, attributes like AMI and instance setype determine the exact configuration of the virtual machine. By mastering attributes, you can fine-tune your HCL configurations to meet precise requirements. Let me walk through a practical example of an HCL resource block. Here, we have a resource block for an Oz EC2 instance. The block type is resource, the label is OSC2, and the contents include two attributes, AMI and instance setype. The AMI attribute specifies the Amazon machine image to use, which is a unique identifier for the operating system and software stack. The instance setype attribute defines the size of the virtual machine, such as T2 micro, which is a common choice for small-scale applications. This block creates a new EC2 instance with the specified settings. Another example is a data block, which retrieves information from an existing resource. In this case, the data block, ASAMI, fetches the latest AMI owned by the user. The attributes most recent and owners control how the data is retrieved, ensuring that the most up-to-date image is selected. These examples illustrate how blocks and attributes work together to define and manage infrastructure. By studying these patterns, you can apply similar structures to other resources and data sources in your configurations. When working with HCL, following best practices ensures that your configurations are clean, readable, and easy to maintain. First, always use consistent indentation to visualize the hierarchy of blocks and attributes. This helps prevent errors and makes the code more approachable for others. Second, choose clear and descriptive labels for your blocks. For example, OSC2 is more informative than Ek 2, especially when multiple resources are involved. Third, avoid hard-coding values directly into your configurations. Instead, use variables or outputs to make your code more flexible and reusable. Hard coding can lead to issues when environments change, but variables allow you to update settings in one place. Finally, add comments to explain complex configurations. While HCL is designed to be readable, some sections may require additional context for future reference. By adhering to these practices, you can create HCL files that are not only functional, but also easy to understand and modify over time. In summary, HCL blocks and attributes form the backbone of infrastructure as code configurations. Blocks organize related settings into logical units, while attributes provide the specific details needed to define those units. The structure of HCL is essential for creating configurations that are both functional and maintainable. Whether you're defining a single resource or a complex system of modules, blocks and attributes work together to ensure clarity and precision. As you continue to work with HCL, remember to apply best practices such as consistent formatting, clear labeling, and the use of variables. These habits will help you build scalable and efficient configurations. The more you practice using blocks and attributes in real-world scenarios, the more comfortable you will become with HCL. By mastering these concepts, you'll be well equipped to manage infrastructure with confidence and efficiency. Variables in HCL serve as temporary storage for data that the program needs to access during execution. This is particularly important in HCL, which is designed for configuration management and infrastructure as code. By using variables, you can create dynamic configurations that adapt to different environments or requirements without rewriting code. For example, a variable might hold a value like a database password or an instance type, which can be changed without altering the core logic of the configuration. This approach enhances reusability, as the same configuration can be applied across multiple projects or environments. It also improves flexibility, allowing developers to adjust parameters easily. Additionally, variables make code maintenance simpler, as changes can be centralized in one place rather than scattered throughout the code base. Declaring variables in HCL is done using the variable block, which provides a structured way to define and such configuration parameters. The basic syntax involves specifying the variable name, followed by a block that includes attributes like type, default value, and description. For instance, a variable named name might be declared with a string type and a default value of guest, ensuring that the configuration has a fallback if no other value is provided. This structure not only clarifies the purpose of each variable, but also enforces constraints. For example, the type attribute ensures that only values of the specified type are accepted, reducing errors. Variables can also include descriptions, which act as documentation for other users or future reference. This practice is especially useful in team environments where multiple people work on the same configuration files. HCL supports several data types, including string, number, Boolean, list, and map, each serving distinct purposes in configuration. A string type is used for text-based values, while a number type handles numeric inputs like port numbers or memory sizes. A Boolean type represents true or false values, often used for conditional logic. Lists and maps allow for more complex data structures, such as a list of ports or a map of tags. For example, a variable named ports could be defined as a list of numbers to specify multiple port values. These data types are essential for ensuring that configurations remain consistent and predictable. Type validation acts as a safeguard, preventing incompatible values from being used. This is critical in infrastructure setups where incorrect data types could lead to configuration failures or security vulnerabilities. Understanding variable scope is crucial for organizing and managing configurations effectively. Local variables are defined within a specific block, such as a module or a resource, and are only accessible within that scope. This limits their influence to a specific part of the code, reducing the risk of unintended side effects. In contrast, global variables are declared at the top level of a configuration file and can be accessed throughout the entire code base. This makes them ideal for values that are reused across multiple resources or modules. Accessing variables in HCL is straightforward, using the syntax var, variable name. This uniform approach ensures that variables are easy to reference and maintain. However, careful attention must be paid to scope to avoid conflicts or overriding values unintentionally. Variables in HCL are assigned values either through default settings or external inputs, such as command line arguments or environment variables. This flexibility allows configurations to be tailored to specific environments or user preferences. For example, a variable like amide might have a default value for testing, but be overridden with a different value when deployed to production. In the context of infrastructure, this means that the same configuration file can be used for multiple instances with minimal changes. The example of an Oz instance resource demonstrates this well, where variables like amide and instance type are used to parameterize the configuration. This approach not only simplifies the setup process, but also ensures consistency across different environments. By centralizing variable values, developers can manage configurations more efficiently and reduce the risk of errors. Adhering to best practices when working with variables in HCL can significantly improve the quality and maintainability of configurations. One key practice is to use descriptive variable names that clearly indicate their purpose. For instance, naming a variable DB password instead of PW makes it immediately clear what the variable represents. Including descriptions in variable definitions also enhances readability and documentation, making it easier for others to understand the configuration. Another important practice is to avoid hard-coding sensitive values, such as passwords or API keys, directly into the configuration files. Instead, these values should be sourced from external secrets management tools or input variables, which can be securely managed and updated without modifying the configuration itself. These practices contribute to more secure, scalable, and manageable infrastructure configurations. In summary, variables are a fundamental component of HCL configurations, enabling dynamic and reusable code. By properly declaring variables with appropriate types and scopes, developers can ensure that their configurations are both reliable and easy to maintain. The use of best practices, such as descriptive naming and externalizing sensitive data, further enhances the robustness of these configurations. As infrastructure becomes increasingly complex, the ability to manage configurations through variables becomes even more critical. Applying these principles not only streamlines the development process, but also supports the creation of clean, scalable, and secure infrastructure setups. With careful planning and adherence to these guidelines, HCL users can build configurations that are both powerful and adaptable to changing requirements. Data types in HCL define the kind of data a variable can hold, which is essential for structuring and organizing information within configurations. This language supports basic types like strings, numbers, and booleans, which are fundamental for representing simple values. For more complex scenarios, HCL includes composite types such as lists, maps, and objects, allowing you to work with structured data efficiently. Understanding these data types ensures that your syntax is correct and helps prevent runtime errors, which can be critical when managing infrastructure configurations. By mastering these concepts, you lay a strong foundation for writing clear and reliable HCL code. The basic data types in HCL include strings, numbers, booleans, and null. A string is textual data enclosed in double quotes, such as hello, and is used to represent characters, labels, or any sequence of text. Numbers can be integers like 42 or floating point values like 3.14, and they are essential for calculations and numerical representations. Booleans, which take the values true or false, are used for logical operations and conditional checks. The null type represents the absence of a value, often useful when a parameter is optional or not yet defined. These basic types form the building blocks for more complex data structures in HCL. Composite data types in HCL allow you to work with collections of values, making it easier to manage structured data. A list is an ordered collection of values, such as 1, 2, 3, and is ideal for sequences where the order matters. A map is an unordered collection of key value pairs, like name equals Alice, which is helpful for associating names with values. Objects similar to maps are used to represent structured data with named attributes, such as id equals 1, name equals Bob, and are commonly used in configuration files. A tuple is a fixed-size collection of values, like 1, a true, and is useful when you need a compact, ordered set of elements. These composite types enable you to model real-world scenarios more effectively. HCL includes various literals to represent data directly in code. String literals are enclosed in double quotes, such as hello HCL, and can include escape sequences for special characters. Number literals can be integers like 42, floating point numbers like 3.14, or even hexadecimal values like 0x1a Boolean literals, are simply true or false, used for logical expressions. The null literal, written as null, indicates the absence of a value. Additionally, HCL supports heretic literals, which allow you to write multi-line strings using the EOF syntax. This is particularly useful for including large blocks of text without worrying about line breaks or escaping characters. HCL differs from other programming languages in several key ways. It prioritizes readability, making the syntax more approachable for humans while still being machine readable. For example, maps and objects are similar, but used differently in configurations. Maps are more flexible for dynamic key-value pairs, while objects are used for structured, named attributes. Lists and tuples are often used interchangeably, but have distinct semantics. Lists are ordered and can be modified, while tuples are fixed in size and content. Unlike some languages, HCL avoids complex type conversions, and explicit casting is rare. This design choice reduces ambiguity and makes configurations more predictable. Data types and literals are the foundation of HCL syntax, enabling you to represent and manipulate data effectively. By understanding these concepts, you ensure clarity and correctness in your infrastructure configurations, which is crucial for reliable automation. Practicing with examples helps reinforce your ability to handle strings, numbers, and structured data confidently. Always validate your configurations to catch type-related errors early, as this can save time and prevent issues in deployment. Mastering these fundamentals will empower you to write robust and maintainable HCL code. An expression in HCL is a combination of values, variables, and operators that evaluates to a single value. This means that any valid expression will resolve to one specific result, whether it is a number, a string, or a Boolean. For example, arithmetic expressions like 3 plus 5 perform calculations. Logical expressions like x greater than 10 evaluate to true or false. And string-based expressions like hello plus world concatenate text. These expressions are the building blocks of programming, allowing developers to perform calculations, compare values, and make decisions within their code. Without expressions, it would be impossible to manipulate data or control the flow of a program. Understanding how expressions work is essential for writing effective efficient HCL code. HCL includes several types of operators, each serving a distinct purpose. Arithmetic operators such as plus, minus, multiply, divide, and modulus are used for numerical calculations. Comparison operators like equals, not equals, greater than, less than, greater than or equal to, and less than or equal to are used to evaluate relationships between values, returning true or false. Logical operators such as and, or, and not allow for combining multiple conditions, enabling complex decision-making. Assignment operators like equals, plus equals, minus equals, multiply equals, and divide equals are used to assign values to variables, often modifying them in place. Finally, bitwise operators such as ampersand, pipe, caret, and tilde operate on binary representations of data, enabling low-level manipulations. Each operator type plays a critical role in constructing functional and expressive HCL programs. Operator precedence in HCL determines the order in which operations are performed within an expression. For instance, multiplication has higher precedence than addition. So 3 plus 5 multiplied by 2 evaluates to 13 rather than 16. Parentheses can override this default order, allowing developers to explicitly define which operations should occur first. This is particularly important in complex expressions where the intended logic might otherwise be misinterpreted. Additionally, logical operators such as and, or have lower precedence than comparison operators, meaning that comparisons are evaluated first in a sequence. Understanding precedence rules helps prevent errors and ensures that expressions behave as intended. Always consider using parentheses to clarify the order of operations, especially in nested or intricate expressions. Expressions are central to conditional logic in HCL, forming the basis of if, else if, and while statements. For example, an if statement might check whether a variable named age is greater than or equal to 18, and whether a variable named has ID is true. This combination of conditions, connected by logical operators like and, allows for precise control over program execution. Expressions also power loops, where a while statement might continue iterating as long as a certain condition remains true. By combining multiple expressions, developers can create sophisticated decision trees and control structures, making their code more dynamic and responsive to varying inputs. Mastering the use of expressions in conditionals is key to writing flexible and robust HCL programs. Common expression errors can lead to unexpected results or program failures. One frequent mistake is missing parentheses in nested expressions, which can alter the intended order of operations. For example, forgetting parentheses in a complex arithmetic calculation might produce an incorrect result. Another error is using the assignment operator equals instead of the comparison operator equals, which can inadvertently change variable values rather than checking for equality. Mixing data types, such as adding a string and a number, can also cause issues, as HCL may concatenate them instead of performing arithmetic. Lastly, overlooking operator precedence can lead to expressions evaluating in a way that contradicts the developer's intent. These errors highlight the importance of careful coding and thorough testing. Practical examples of expressions in HCL illustrate their versatility and utility. An arithmetic expression like total equals price multiplied by quantity plus tax demonstrates how values are calculated and combined. A comparison expression such as is eligible equals age greater than 18 and country equals USA shows how multiple conditions can be evaluated simultaneously. Assignment expressions like counter plus equals 1 simplify updating variable values, equivalent to counter equals counter plus 1. String concatenation examples such as greeting equals hello plus name highlight how text can be dynamically assembled. These examples reflect how expressions are used daily in HCL to process data, make decisions, and construct meaningful outputs. Expressions and operators are fundamental to manipulating data and controlling program flow in HCL. Their proper use ensures that code functions as intended, while misunderstandings can lead to bugs and inefficiencies. Understanding operator precedence and the correct application of each operator type is crucial for writing accurate and maintainable code. Practicing the creation and debugging of expressions helps reinforce these concepts, enabling developers to write more sophisticated and reliable programs. By mastering expressions, HCL programmers can unlock greater flexibility and precision in their work, ultimately improving the quality and performance of their software. Conditional logic is a fundamental concept in programming that allows software to make decisions based on specific criteria. Imagine a program as a decision tree where each branch represents a different outcome based on whether a condition is true or false. This capability enables programs to handle dynamic data, respond to user input, and adapt to changing environments. For example, a program might check if a user's input meets certain requirements before proceeding, or it might adjust its behavior based on the current system state. By incorporating conditional logic, developers can create more flexible and responsive applications that handle a wide range of scenarios. At the heart of conditional logic in HCL are if-else statements, which form the basis for decision-making in code. These statements evaluate a condition and execute different blocks of code depending on whether the condition is true or false. The structure is straightforward. If the condition is true, the code within the if block runs. Otherwise, the code in the else block executes. This allows for branching paths in a program, enabling it to handle multiple possibilities. For instance, a program might check if a user is logged in and then either grant access or prompt for credentials. If-else statements are essential for creating programs that can react to different situations dynamically. The syntax for if-else statements in HCL follows a clear structure. It begins with the keyword if, followed by a condition enclosed in parentheses. If the condition evaluates to true, the code within the first set of curly braces executes. If not, the else block runs. Here is an example. If condition, code to execute. If condition is true, else, code to execute. If condition is false. This structure supports nested if-else statements, where multiple conditions are checked sequentially, and logical operators such as and, or, and not can combine conditions. Logical operators allow for complex decision-making, such as checking if two conditions are simultaneously true, or if at least one of several conditions is met. To build effective conditional statements, developers use a variety of operators. Comparison operators like equals, not equals, greater than, less than, greater than or equal to, and less than or equal to help compare values. Logical operators such as and, or, and not allow for combining or modifying conditions. For example, a program might use the and operator to check if two conditions are both true, or the or operator to check if at least one condition is true. These operators provide the tools to create precise and flexible conditions, ensuring that programs can handle complex decision-making scenarios with accuracy. Nested if-else structures allow programs to handle multiple conditions in a sequential manner. This approach is particularly useful when there are several possible outcomes. For example, a program might first check if a user is logged in, then check their role, and finally determine their access level. The structure for this is if condition 1, code else if condition 2, code else, code. By chaining conditions, developers can create a single decision tree that covers various scenarios without duplicating code. This method enhances clarity and efficiency, making it easier to manage complex logic in a program. When working with conditional logic, following best practices ensures that code remains readable and maintainable. First, keep conditions simple and avoid overly complex expressions that are hard to understand. Second, always use curly braces even for single-line statements to prevent errors that can arise from missing braces. Third, minimize excessive nesting by using else if statements instead of multiple if-else blocks, which improves readability. Finally, test edge cases such as boundary values or unexpected inputs to ensure the program behaves as intended under all conditions. These practices lead to more robust and reliable code. Conditional logic has numerous real-world applications that highlight its importance in software development. For instance, it is used to validate user input, such as checking if a form field is empty or if a password meets specific criteria. It also controls program behavior based on environmental factors, like adjusting settings depending on the operating system or user preferences. Rule-based systems, such as scoring algorithms in games or grading systems, rely on conditional logic to apply different rules based on input data. Additionally, dynamic data filtering and processing, such as sorting or categorizing information, depend on conditions to determine how data is handled. These applications demonstrate the versatility of conditional logic in solving practical problems. In summary, conditional logic and if-else statements are foundational elements of programming in HCL, enabling decisions based on specific criteria. They allow programs to branch into different execution paths, making software more adaptable and responsive. Mastering these concepts is crucial for developing flexible and functional applications. By practicing the creation and debugging of conditional blocks, developers can enhance their proficiency and build more sophisticated programs. As with any skill, consistent practice and attention to best practices will lead to greater confidence and effectiveness in using conditional logic. Loops are a fundamental concept in programming that allow you to execute a block of code multiple times. In HCL, loops enable you to repeat specific tasks without having to write the same code over and over again. This is particularly useful when working with sequences, collections, or data structures that require repetitive operations. Iteration, the process of going through each element in a data structure, is a key part of this. Whether you're processing a list of items, looping through a range of numbers, or performing actions based on conditions, loops make these tasks efficient. The three main loop types in HCL are for loops, while loops, and do-while loops. Each of these has unique use cases and can be applied depending on the specific requirements of your program. Understanding how to use these loops effectively is essential for writing clean and maintainable HCL code. HCL provides several loop structures to handle different scenarios. The for loop is typically used when you need to iterate over a collection or a range of values. It allows you to specify a variable that takes on each value in the collection, making it ideal for tasks like processing lists or arrays. The while loop, on the other hand, continues to execute as long as a given condition remains true. This is useful when the number of iterations is not known in advance. The do-while loop is similar to the while loop, but ensures that the code block runs at least once before checking the condition. This can be helpful in situations where you need to perform an action once and then check if it should continue. Additionally, HCL supports nested loops, which means you can place one loop inside another. This is particularly powerful when working with multidimensional data or complex iteration patterns. The syntax for a for loop in HCL is straightforward and easy to understand. You start by defining a variable that will represent each element in the collection. Then, you specify the collection or range you want to iterate over. The code block inside the loop is executed for each element. For example, if you have a list of strings, the for loop can process each string one by one. When working with numerical ranges, HCL provides the range function, which allows you to generate a sequence of numbers. This is useful for tasks like counting from one number to another, or repeating an action a specific number of times. It's important to note that the variable in the for loop is scoped to the loop itself, which helps prevent unintended side effects. By mastering the for loop, you can efficiently handle a wide variety of iteration tasks in HCL. The while loop in HCL is designed to execute a block of code repeatedly as long as a specified condition evaluates to true. Unlike the for loop, which is typically used for iterating over known collections, the while loop is more suited for situations where the number of iterations is not predetermined. For instance, you might use a while loop to keep processing user input until a certain exit condition is met. The structure of a while loop is simple. You define the condition, and the code block runs as long as that condition remains true. However, it's crucial to ensure that the condition eventually becomes false to avoid infinite loops. To prevent this, you must update the variables involved in the condition within the loop body. Testing and debugging while loops carefully is essential to ensure they behave as expected. Iteration in HCL extends beyond simple lists and arrays. You can also iterate over maps, which are collections of key value pairs. When looping through a map, you can access both the key and the value, allowing you to perform operations based on specific criteria. For example, you might sum all the values in a map or check if a particular key exists. Similarly, when working with lists and arrays, you can loop through each element to modify, filter, or analyze the data. HCL also supports control flow statements like break and continue, which give you more flexibility in managing loop execution. The break statement allows you to exit a loop prematurely when a certain condition is met, while the continue statement skips the remaining code in the current iteration and moves to the next one. These tools are invaluable for handling complex iteration scenarios. When working with loops in HCL, it's important to follow best practices to ensure your code is efficient and error-free. One of the most common pitfalls is creating infinite loops, which can cause your program to hang or crash. To avoid this, always make sure that the loop condition will eventually become false. This often involves updating variables or changing states within the loop body. Using the break statement can help exit loops when specific conditions are met, but it should be used judiciously to maintain readability. Keeping your loop logic simple and well-structured is also crucial, as complex loops can be difficult to debug. Additionally, testing edge cases, such as empty collections or unexpected input, can help identify potential issues before they become problems. By adhering to these practices, you can write more reliable and maintainable HCL code. In conclusion, loops and iteration are essential tools for any HCL programmer. They allow you to automate repetitive tasks, process data efficiently, and create dynamic programs that respond to changing conditions. Mastering the for, while, and do-while loops gives you the flexibility to handle a wide range of scenarios, from simple iterations to complex nested structures. By following best practices and being mindful of potential pitfalls, you can write code that is both effective and easy to maintain. As with any programming concept, the key to proficiency is practice. Applying these techniques to real-world examples will help reinforce your understanding and improve your ability to solve problems using HCL. Whether you're processing data, building configurations, or automating workflows, loops will be a valuable part of your programming toolkit. Functions in HCL are reusable blocks of code that perform specific tasks, allowing developers to break down complex problems into manageable pieces. By encapsulating logic within functions, you can enhance code modularity, which means each part of your code has a single responsibility. This makes your code easier to understand, test, and maintain. Functions also promote reusability, so you can use the same code across different parts of your project without rewriting it. For example, a function might take parameters like a string or a number and return a result. Common built-in functions in HCL include length, which counts elements in a list, lower, which converts text to lowercase, and format, which helps construct strings dynamically. These functions streamline tasks and reduce the need for repetitive code. To define a function in HCL, you use the function keyword followed by the function name and parentheses containing parameters. The syntax is straightforward. Function name parameters body. Parameters in HCL are passed as key-value pairs, which means you specify values by their names rather than their positions. This approach makes the code more readable and less error-prone. For instance, a function called greet might accept a parameter named name and return a greeting string. The body of the function contains the logic, such as combining the parameter with a static string. This structure allows you to create flexible and reusable code that can adapt to different inputs. In HCL, function arguments are always passed by name, not by position, which ensures clarity and reduces the risk of mistakes. When you call a function, you explicitly assign values to parameters using their names. This is particularly useful when a function has many parameters, as it avoids confusion about which value corresponds to which argument. Return values are explicitly defined using the return keyword, which means the function must explicitly state what it outputs. Functions in HCL can return a variety of data types, including strings, numbers, lists, or maps. For example, a function that adds two numbers would return the sum, while a function that combines data might return a structured map. This flexibility allows functions to handle diverse tasks efficiently. HCL provides a rich set of built-in functions to simplify common operations. These functions are categorized into areas like string manipulation, type conversion, and data aggregation. String manipulation functions, such as lower and upper, help adjust text formatting. Type conversion functions, like converting a string to a number, ensure data compatibility. Data aggregation functions, such as length, allow you to analyze collections. These built-in tools are designed to handle typical programming needs, reducing the need for custom code. By using these functions, developers can write cleaner, more concise scripts that are easier to debug and maintain. Some of the most frequently used built-in functions in HCL include length, lower, upper, and format. The length function returns the number of elements in a list, which is useful for validating data size or controlling loops. The lower function converts a string to lowercase, making it ideal for case-insensitive comparisons. Similarly, the upper function transforms text to uppercase, which might be needed for formatting or matching specific requirements. The format function allows you to create dynamic strings by inserting values into placeholders. For example, you could use it to generate a personalized message by replacing a placeholder with a user's name. These functions are essential for handling text and data efficiently. Advanced built-in functions in HCL offer powerful capabilities for working with complex data structures. The merge function combines two maps into a single map, which is useful for consolidating configuration settings. The lookup function retrieves a value from a map, and if the key is not found, it can return a default value, preventing errors. The template function generates a string based on a predefined template and a set of values, making it easier to create dynamic content. Finally, the join function concatenates elements of a list into a single string, separated by a specified character. These functions enable developers to manipulate and transform data with minimal code, improving productivity and reducing complexity. Practical examples illustrate how built-in functions simplify real-world tasks. For instance, the length function can determine the size of a list, which is helpful when validating input or iterating through elements. The format function allows you to construct strings dynamically, such as creating a message that includes a user's name. The merge function combines two maps, which might be used to merge default configurations with user-specific settings. These examples show how functions can streamline workflows, reduce redundancy, and make code more adaptable. By leveraging these tools, developers can focus on solving problems rather than writing repetitive code. When working with functions in HCL, following best practices ensures your code remains clear and maintainable. Start by using descriptive names that reflect the function's purpose, such as calculate total instead of calc. Avoid overcomplicating nested functions, as this can lead to confusion and bugs. Instead, keep functions focused on a single task. Leverage built-in functions whenever possible, as they are optimized and tested. Finally, document your functions with comments or explanations, so others can understand their role and usage. These practices not only improve code quality, but also make collaboration easier, especially in team environments. Functions and built-in functions are fundamental to writing efficient and readable HCL scripts. They allow you to organize code logically, avoid repetition, and handle complex operations with ease. By mastering these concepts, you can create configurations that are easier to manage, update, and scale. Whether you're working on simple scripts or large-scale projects, functions provide the building blocks for structured and maintainable code. The key to success is practice. Apply these concepts to real-world scenarios to gain confidence and proficiency. With time, you'll find that functions become an indispensable part of your HCL toolkit, Modules in HCL serve as building blocks for organizing infrastructure code, allowing developers to create reusable components that streamline the management of complex systems. By encapsulating configurations, variables, and outputs, modules act as self-contained units that handle specific tasks or resources. This approach not only reduces the need for repetitive code across projects, but also ensures that changes can be made in one place, which then propagate throughout the system. The modularity of HCL modules promotes a structured and maintainable code base, making it easier to scale and manage infrastructure as it grows. Reusable code in HCL significantly enhances efficiency by eliminating the need to write the same code multiple times across different projects. When code is centralized within modules, updates and maintenance become straightforward, as changes only need to be made in one location. This consistency ensures that deployments across environments remain uniform, reducing the risk of errors. Furthermore, reusable code fosters collaboration among teams by providing a standardized structure, which makes it easier for developers to understand, contribute to, and extend existing infrastructure configurations. Creating a module in HCL involves defining a module block with a name and a source path, which points to the directory containing the module's code. For example, the syntax module example source equals example module demonstrates how to reference a module located in a subdirectory. Modules can accept inputs through variables, allowing them to be customized for different use cases, and they can return outputs to share values with the parent configuration. To maintain clarity, it is best practice to structure modules in separate directories, ensuring that the code base remains organized and easy to navigate. Modules in HCL rely on inputs and outputs to interact with their parent configurations. Inputs, defined using the variable block, act as parameters that allow modules to be tailored for specific requirements. For instance, a variable region with a string type can be used to specify the geographic location of resources. Outputs, on the other hand, expose values from a module so that they can be accessed by other parts of the infrastructure. An example of this is the output VPSID that returns the ID of a virtual private cloud. During deployment, values for these inputs can be passed using the Terraform apply command, enabling dynamic flexible infrastructure setups. To maximize reusability, HCL modules should adhere to several best practices. First, each module should focus on a single responsibility, ensuring that it remains simple and easy to manage. Descriptive names for modules and variables help clarify their purpose, making the code more readable. Comprehensive documentation is essential, as it guides users on how to use the module and what inputs or outputs are required. Finally, versioning modules with tags like V100 ensures that changes are tracked and that different projects can use stable, tested versions of the same module. Module versioning is critical for maintaining stability and compatibility across projects. By using version tags, developers can control which version of a module is used, preventing unintended changes from breaking existing configurations. The Terraform Get command allows modules to be updated to the latest version, but it is crucial to test these updates in isolated environments before deploying them. Public modules should avoid breaking changes to ensure that dependent projects continue to function correctly. This practice fosters trust and reliability when sharing modules with others. In real-world scenarios, HCL modules are invaluable for creating consistent and scalable infrastructure. For example, a reusable Oz VPC module can be configured for different regions, ensuring that network settings are standardized across locations. A database module might include customizable parameters such as instance size or storage capacity, allowing it to adapt to various workloads. Teams can share modules to maintain uniformity in their infrastructure setups, while third-party modules from the Terraform registry provide pre-built solutions for common tasks. These use cases demonstrate how modules enhance productivity and reduce the risk of configuration errors. In summary, modules in HCL are essential for managing infrastructure code efficiently and effectively. They promote reusability, which saves time and effort while ensuring consistency across deployments. Well-structured modules improve collaboration by providing clear and organized code, making it easier for teams to work together. By following best practices such as versioning and documentation, developers can maintain reliable and scalable infrastructure. Embracing modules in HCL transforms complex infrastructure management into a more manageable and predictable process, Organizing code with multiple files is a fundamental practice in software development that enhances the way we build and maintain programs. When we write code, especially for large projects, it's essential to break down the work into manageable pieces. Modular code allows us to isolate specific tasks, making it easier to debug, test, and update. For example, if a program has a section for handling user input and another for processing data, separating these into different files ensures that changes in one area don't accidentally affect the other. This approach also scales better as projects grow, enabling teams to work on different parts simultaneously without conflicts. In HCL, the way we structure files is designed to support this modularity, allowing developers to create clean, organized, and efficient code bases. A module in HCL is a way to group related code together, much like how a library organizes books by subject. Each file in HCL can act as a module, encapsulating specific functionality. For instance, a file named MathUtils. HCL might contain functions for mathematical operations like addition or multiplication, while a file called DataLoader HCL could handle tasks like reading from a database or parsing files. This separation ensures that code is self-contained and easier to navigate. By organizing code this way, developers can quickly locate the right file for a task, reducing the time spent searching through large code bases. Additionally, modules promote reusability, as the same code can be imported into multiple projects without duplication. When structuring files, it's crucial to follow best practices to maintain clarity and avoid confusion. One key principle is to separate logic based on functionality. For example, all code related to user authentication should reside in one file, while code for handling network requests goes into another. Consistent naming conventions are equally important. Using a pattern like feature rename, HCL makes it easy to identify the purpose of a file at a glance. For instance, a file named user authentication, HCL immediately tells a developer what it contains. Another critical practice is to avoid global variables, which can lead to unexpected behavior when multiple files interact. By limiting the scope of variables and functions, we reduce the risk of conflicts and make the code base more predictable. Including files in HCL is a straightforward process that allows developers to reuse code across different parts of a project. The syntax for including a file is include file name HCL, which tells the compiler to merge the contents of that file into the current one during compilation. For example, if you have a file called constants, HCL that defines important values like maximum user count or default timeout, you can include it in multiple files without rewriting the same code. This not only saves time, but also ensures consistency as changes to constants. HCL automatically propagate to all files that include it. It's a powerful tool for maintaining a single source of truth for shared data. Functions that span multiple files require careful planning to ensure they work seamlessly together. The standard approach is to declare functions in a header file, such as functions HCL, which acts as a blueprint for what the function does. Then, the actual implementation of the function is written in a separate file, like function simple HCL. This separation allows developers to see the function's purpose without getting lost in the details of how it works. It also makes it easier to update or replace the implementation without affecting other parts of the code. However, it's vital that the function signatures, such as the number and type of parameters, match exactly across files. Mismatches can lead to errors that are difficult to trace, so careful attention to detail is necessary. Managing dependencies between files is essential to prevent issues like circular references, where two files depend on each other in a way that creates a loop. For example, if file A includes file B and file B includes file A, the compiler might struggle to resolve the relationships, leading to errors. To avoid this, developers should track dependencies carefully, ensuring that each file only includes what it absolutely needs. HCL provides mechanisms like import or require statements to handle these relationships explicitly. Additionally, documenting file relationships through comments or diagrams helps other developers understand how different parts of the code base interact. Clear documentation reduces the risk of accidental misuse and makes the project easier to maintain over time. In summary, organizing code into multiple files is a cornerstone of effective software development. It improves readability by breaking down complex systems into smaller, focused components. Collaboration becomes smoother when code is structured logically, as team members can work on separate files without stepping on each other's toes. by following HCL's file structure guidelines, developers ensure consistency across projects, making it easier to onboard new members or scale existing systems. Ultimately, adopting a modular design mindset leads to more scalable, efficient, and maintainable programs. As you work on your HCL projects, remember that thoughtful organization today saves time and effort tomorrow. Terraform is an infrastructure as code tool that allows you to provision and manage cloud resources through code. This means instead of manually configuring cloud services, you write code to define your infrastructure, making it repeatable, versionable, and scalable. HCL, or HashiCorp Configuration Language, is the primary language used in Terraform to describe these configurations. It is designed to be human-readable and structured, which makes it easier to manage complex infrastructure setups. This session will focus specifically on working with Terraform resources using HCL syntax. We will explore how to define resources, structure configurations, and leverage HCL to create efficient and maintainable infrastructure code. A Terraform resource represents any manageable entity in a cloud environment, such as an AWS EC2 instance, an Azure virtual machine, or a Google Cloud storage bucket. Each resource is a logical component that Terraform can create, update, or delete. These resources are defined using blocks in HCL, which provide a clear structure for specifying the type, name, and configuration of the resource. For example, the block resource ausinstance example defines an Oz EC2 instance with the name example. This syntax ensures that each resource is uniquely identifiable, and its properties are explicitly outlined, which is crucial for accurate infrastructure management. The structure of a Terraform resource block in HCL includes several key components. First, the provider specifies the cloud service you are working with, such as Oz for Amazon Web Services or Azureum for Azure. Next, the type identifies the specific resource you are defining, like instance for a virtual machine or bucket for a storage container. The name serves as a unique identifier for the resource within your configuration, allowing Terraform to reference it later. Finally, the configuration section contains attributes and arguments that define the resource's properties, such as instance type, region, or storage size. Together, these elements form the foundation of Terraform's declarative approach to infrastructure management. When defining a Terraform resource, you will encounter 3 types of attributes: required, optional, and computed. Required attributes are essential for the resource to function and must be specified in the configuration. For example, an EC2 instance requires a valid AMI ID and instance type. Optional attributes allow you to fine-tune the resource's behavior, such as setting a count to create multiple instances or using depenson to manage dependencies. Computed attributes, on the other hand, are values that Terraform determines during execution, like the public IP address of an instance. Understanding these attributes helps you build flexible and robust infrastructure configurations. Managing resource dependencies is critical when working with Terraform, as some resources may rely on others being created first. The depenson argument explicitly enforces this order, ensuring that Terraform creates or destroys resources in the correct sequence. For example, if a database instance depends on a virtual private cloud, you can use depenson equals OSP example to guarantee the VPC is set up before the database. Terraform also automatically detects dependencies by analyzing references between resources, such as linking an EC2 instance to a security group. This combination of explicit and implicit dependency management ensures your infrastructure is built reliably and efficiently. Modules are a powerful feature in Terraform that allow you to encapsulate and reuse configurations across projects. By organizing related resources into a module, you can maintain a clean and modular code base, reducing duplication and improving scalability. For instance, a VPC module might include subnets, root tables, and security groups, which can be reused across multiple environments. To include a module in your configuration, you use a module block, specifying the source path and any required variables. For example, module VPC source /modules/VPC tells Terraform to load the VPC configuration from a local directory. This approach promotes consistency and simplifies complex infrastructure setups. To write effective Terraform configurations, it's important to follow best practices that enhance readability, maintainability, and efficiency. One key principle is to keep your code dry, or don't repeat yourself, by using variables to store common values like region or instance types. This reduces redundancy and makes updates easier. Organizing resources into modules also improves scalability, allowing you to manage large infrastructures more effectively. Additionally, always use the Terraform apply command to review changes before they are applied, ensuring you understand the impact of your configurations. These practices help you create reliable, reusable, and well-structured infrastructure code. In summary, Terraform resources in HCL provide a powerful and flexible way to manage infrastructure through code. By leveraging the structured syntax of HCL, you can define, organize, and maintain cloud resources with clarity and precision. Understanding resource blocks, attributes, and modules is essential for building scalable and efficient infrastructure configurations. As you continue to practice defining and managing resources, you will gain confidence in using Terraform to automate and streamline your cloud operations. Remember, the key to mastering Terraform lies in consistent practice and a deep understanding of its core concepts. Managing outputs in HCL is essential for ensuring that your programs communicate effectively with users, systems, and other modules. Outputs act as the bridge between your code and the external world, allowing you to display results, log events, or pass data between components. When you understand how to control these outputs, you gain greater insight into your program's behavior and can troubleshoot issues more efficiently. Exported values play a critical role in this process by enabling modularity and reusability. By defining and exporting specific variables or functions, you allow other parts of your code base to access and utilize these elements without duplicating effort. The key objectives of this section are to define outputs clearly, capture them during execution, and leverage them strategically to enhance the functionality of your HCL programs. In HCL, outputs can take several forms, each serving a distinct purpose. Standard outputs, such as those generated by print or log functions, are used to display immediate results or messages during program execution. These are invaluable for real-time feedback and debugging. File-based outputs, on the other hand, involve writing data to external files like text documents or comma-separated values files, which is useful for storing large datasets or generating reports. Log files, a subset of file-based outputs, are specifically designed for tracking program activity over time, making them essential for auditing and debugging. By understanding the differences between these output types, you can choose the most appropriate method for your needs, ensuring data is accessible, organized, and reliable. Controlling output streams in HCL allows you to direct where your program's data goes, which is crucial for managing complexity. The greater than symbol or the double greater than symbol can be used to redirect outputs to files, appending or overwriting content as needed. This is particularly useful for capturing logs or saving results without cluttering the terminal. Conditional outputs add another layer of control, enabling your program to generate specific messages based on its current state or user input. For example, you might display an error message only if a certain condition is met. Additionally, integrating try-catch blocks into your output operations ensures that any errors during these processes are handled gracefully, preventing unexpected crashes and maintaining program stability. Exported values in HCL extend the reach of your code by making specific variables or functions available to other modules. This is achieved using the export keyword, which signals to the HCL interpreter that these elements should be accessible beyond their original scope. However, it's important to be mindful of scope limitations. Overusing exports can lead to conflicts or make your code harder to maintain. Best practices for modular design include exporting only what is necessary, organizing exports logically, and documenting their purpose. By doing so, you create a cleaner, more efficient code base that is easier to scale and collaborate on, ensuring that each module remains self-contained, yet interconnected. Practical examples of exported values demonstrate their power in real-world scenarios. For instance, exporting a function to another module allows that function to be reused across different parts of your program, reducing redundancy and improving consistency. Sharing configuration values, such as API keys or database credentials, across scripts ensures that changes are made in a single place, minimizing errors. Dynamic data retrieval is another key application, where exported values can be used to fetch information from external sources, such as databases or APIs, based on user input or system state. These examples highlight how exported values act as a foundation for building flexible, responsive, and maintainable HCL programs. Adhering to best practices for output management ensures your HCL programs are both effective and maintainable. Documenting output formats and expected values is critical for clarity, especially when working in teams or revisiting code later. Avoiding redundant or excessive outputs keeps your program's communication clean and focused, preventing information overload. Testing outputs thoroughly is equally important. This includes verifying that data is written correctly. Logs capture relevant details, and exported values function as intended. By following these practices, you create a more reliable and efficient code base, reducing the risk of errors and making future modifications easier. In summary, outputs and exported values are fundamental to the functionality and reusability of HCL programs. Properly managing outputs ensures that your code communicates effectively and remains easy to debug and maintain. Exported values, when used thoughtfully, enable modular design and collaboration, allowing different parts of your program to work together seamlessly. By applying best practices such as documentation, efficiency, and testing, you can optimize the performance of your HCL programs, making them more robust and scalable. These principles will help you build code that is not only functional, but also adaptable to future needs. HCL stands for HashiCorp Configuration Language, and it is a specialized programming language designed to define and manage infrastructure as code. This means that instead of manually configuring cloud resources or systems, you can write declarative configurations that describe the desired state of your infrastructure. HCL simplifies the process by allowing you to specify what you want rather than how to achieve it, which reduces errors and increases efficiency. Tools like Terraform, Packer, and Vault leverage HCL to automate the provisioning and management of cloud resources, services, and systems. Whether you're setting up virtual machines, storage buckets, or security policies, HCL provides a consistent and scalable way to handle infrastructure tasks across different platforms. HCL providers are essential components that act as bridges between your HCL configurations and external services or APIs. These plugins enable HCL to interact with cloud platforms, third-party services, and other systems by translating your configuration into actionable commands. For example, when you write a configuration for an AWS EC2 instance, the AWS provider handles the communication with AWS's API to create that instance. Similarly, the Kubernetes provider allows you to manage containerized applications by translating HCL directives into Kubernetes API calls. Without providers, HCL would be limited to local or internal systems, making it impossible to leverage the vast ecosystem of cloud and infrastructure services. The role of HCL providers is multifaceted and critical to the success of infrastructure automation. First, they manage resources by creating, updating, and deleting them based on your configurations. This includes everything from virtual machines and storage, accounts, to complex services like databases and networking components. Second, providers handle authentication by securely managing credentials and access controls, ensuring that your configurations can interact with external services without exposing sensitive information. Third, they act as intermediaries for API interactions, converting HCL syntax into the specific API requests required by cloud providers. Finally, providers play a key role in state management, tracking the current state of resources to maintain consistency and enable versioning, which is crucial for collaboration and rollback scenarios. Several common HCL providers are widely used across different platforms. The AWS provider is one of the most popular, allowing you to manage resources like EC2 instances, S3 buckets, and IAM roles. The Azure provider enables similar capabilities for Microsoft's cloud ecosystem, including virtual networks, storage accounts, and virtual machines. The Kubernetes provider is essential for deploying and managing containerized applications, handling tasks like cluster creation and service deployment. Lastly, the Terraform provider serves as a bridge for integrating HCL with Terraform, allowing for multi-cloud workflows that span different infrastructure providers. Each of these providers is tailored to the specific APIs and requirements of their respective platforms, making it easier to manage complex environments. HCL providers operate by being explicitly referenced in your configurations through provider blocks. These blocks define which provider to use and its specific settings, such as authentication details or region parameters. When When you run commands like terraform apply, the provider validates your configuration to ensure it is syntactically correct and aligns with the expected parameters. Once validated, the provider interacts with the corresponding API to create, update, or delete resources. This process also involves resolving dependencies, ensuring that resources are created in the correct order to avoid conflicts. For instance, a virtual machine might require a subnet and a virtual network to exist first, and the provider ensures this sequence is followed automatically. To use HCL providers effectively, it is important to follow best practices that enhance security, stability, and maintainability. One key practice is to use versioned providers, which ensures that your configurations work consistently across different environments and avoids unexpected changes from newer versions. Securing credentials is another critical step, as providers often require access keys or tokens. Instead of hard-coding these in HCL files, use environment variables or secret management tools like HashiCorp Vault. Avoiding hard-coded sensitive data reduces the risk of exposure in case of misconfigurations or leaks. Finally, regularly updating providers is essential to take advantage of new features, performance improvements, and security patches, ensuring your infrastructure remains robust and up to date. In summary, HCL providers are fundamental to the functionality of the HashiCorp configuration language, enabling it to interact with a wide range of external systems and services. By abstracting the complexity of API interactions, providers simplify infrastructure management, making it more accessible and efficient. They allow teams to focus on defining their desired infrastructure state rather than the intricate details of API calls or resource dependencies. Mastering HCL providers empowers users to build scalable, secure, and automated cloud solutions, ultimately transforming how organizations manage their digital infrastructure. Whether you are working with a single cloud provider or a multi-cloud environment, understanding and leveraging providers is essential for achieving reliable and repeatable infrastructure automation. Welcome to the section on advanced variable management in HCL. Today, we will explore techniques that elevate your ability to optimize variable usage in complex programs. Efficient variable handling is critical because it directly impacts performance, readability, and maintainability of code. mismanaged variables can lead to memory issues, bugs, and inefficient execution. By mastering scope, memory, and dynamic strategies, you will gain the tools to write cleaner, more reliable, and scalable HCL programs. Let's begin by understanding how variable scope and lifetime influence code structure. Variable scope defines where a variable can be accessed within a program. Local variables are confined to specific functions or blocks, reducing the risk of unintended modifications. Global variables, on the other hand, are accessible throughout the entire program, but can introduce side effects if not managed carefully. Block-scoped variables, introduced in modern HCL versions, allow you to limit visibility to a specific code block, enhancing modularity and reducing conflicts. Lifetime management refers to the duration a variable exists in memory. For instance, local variables are created when a function is called and destroyed when it exits, while global variables persist for the program's entire runtime. Understanding these concepts ensures you control resource usage and avoid unexpected behavior. Memory management in HCL involves balancing manual and automatic allocation. Manual allocation gives you precise control, but requires careful cleanup to prevent memory leaks, where unused memory is not released. Automatic allocation, such as garbage collection, simplifies this process by reclaiming memory when variables are no longer referenced. However, relying solely on automatic methods may not always be optimal. To avoid leaks, always ensure variables are properly deallocated when their scope ends. Garbage collection in HCL works by identifying and freeing unreachable objects, but understanding its behavior helps you write more efficient code. Combining both approaches strategically can lead to robust memory usage patterns. Dynamic variable handling allows you to create and modify variables at runtime, offering flexibility in data manipulation. This is particularly useful in scenarios where variable names or values are determined during program execution. Pointers in HCL enable direct memory access, allowing you to modify data structures dynamically. However, this power requires caution to avoid undefined behavior. Best practices include using descriptive names for dynamically created variables and avoiding overly complex naming schemes that reduce readability. By leveraging dynamic techniques, you can build adaptable systems that respond to changing requirements without hard-coding values. Constants and immutable variables are essential for ensuring data integrity. Declaring a constant in HCL prevents its value from being altered after initialization, which is vital for values like configuration settings or mathematical constants. Immutability reduces bugs caused by unintended changes and makes code easier to reason about. In HCL, constants are typically defined using specific keywords, and their scope follows similar rules to variables. Rules for using constants include avoiding their use for values that may change and ensuring they are initialized at declaration. Embracing immutability leads to more predictable and maintainable code. Advanced variable typing in HCL includes type inference and explicit typing. Type inference allows the compiler to deduce variable types based on assigned values, reducing boilerplate code. Explicit typing, however, improves clarity and enforces strict type checks, preventing errors. Type safety is a cornerstone of reliable programming, as it catches mismatches early. For specialized needs, HCL supports custom data types, enabling you to define structures tailored to your application's requirements. By combining these approaches, you can balance flexibility with precision, ensuring your code is both efficient and robust. Best practices for variable management begin with consistent naming conventions. Use descriptive names that reflect a variable's purpose, such as user input instead of X. Avoid global variables whenever possible, as they can create hidden dependencies and make debugging difficult. When necessary, limit their scope and document their use. Comments should explain the intent behind variables, especially in complex logic. For example, a variable named counter might need a comment if its increment logic is non-trivial. These practices enhance collaboration and make your code easier to maintain over time. In summary, advanced variable techniques in HCL revolve around scope, memory, and dynamic handling. Mastering these areas ensures your code is efficient, readable, and scalable. By applying strategies like block scoping, garbage collection, and immutable variables, you can write programs that are both powerful and maintainable. Remember to prioritize clarity in naming, minimize global variables, and leverage HCL's typing features. These practices will not only improve your code, but also make you a more effective developer. Thank you for your attention, and I encourage you to experiment with these concepts in your projects. Hello, everyone. Today, we will explore the fundamentals of HCL code structure. HCL, or HashiCorp Configuration Language, is a domain-specific language designed to define infrastructure as code. It allows developers and DevOps engineers to model and provision infrastructure in a declarative way. The importance of structured code cannot be overstated. Well-organized code enhances readability, making it easier for teams to collaborate. It improves maintainability by reducing the risk of errors during updates. Scalability is also critical, as structured code adapts more efficiently to growing infrastructure needs. By the end of this session, you will understand best practices for organizing HCL code, ensuring your configurations are clean, efficient, and easy to manage. Modularization and reusability are key to effective HCL practices. Breaking code into reusable modules promotes consistency across projects and reduces duplication. By using module blocks, you can encapsulate resources and configurations, making them self-contained and easier to manage. For example, a module for a virtual machine can be reused across different environments. Avoiding hard-coded values is essential. Instead, leverage variables and outputs to make configurations flexible. This approach allows you to adjust settings without modifying the core logic, enhancing adaptability. By prioritizing modularity, you create a library of reliable components that streamline development and reduce errors. Consistent naming conventions are vital for clarity and collaboration. In HCL, it is recommended to use lowercase letters with underscores to separate words, such as VM instance or database connection. This standardization ensures that variables, modules, and resources are easily identifiable. A standardized naming pattern also helps teams quickly understand the purpose of each element. For instance, a module named Network Security Group clearly indicates its function. Avoid ambiguous names like temp or config, which can lead to confusion. Clear and descriptive names improve the overall maintainability of your code base, making it accessible to all team members. Proper indentation and formatting are essential for readability. Consistent indentation such as 2 or 4 spaces, helps visualize nested blocks and logical structures. For example, indenting resource blocks under a module makes the hierarchy clear. Line breaks should separate logical sections, such as variables, resources, and outputs, creating a visual structure that is easier to navigate. Automated tools like HCL linters or formatters can enforce these standards, ensuring uniformity across the code base. By maintaining clean formatting, you reduce the cognitive load for anyone reviewing or modifying the code, leading to fewer errors and faster development cycles. Documentation and comments are critical for explaining complex logic and non-obvious configurations. Inline comments using the hash symbol can clarify specific lines, while multi-line comments enclosed in /* and // provide detailed explanations. For instance, a comment might explain why a particular resource configuration is necessary. Documenting module inputs, outputs, and resource purposes ensures that others understand how to use and extend your code. This practice is especially valuable in collaborative environments where clarity prevents misunderstandings and accelerates onboarding for new team members. Error handling and validation are crucial for robust HCL configurations. Validation blocks allow you to enforce constraints on input values, ensuring they meet specific criteria. For example, a validation rule might check that a variable is a positive integer. Implementing try and catch mechanisms helps manage errors gracefully, preventing configurations from failing abruptly. Testing configurations with HCL or Terraform commands enables early detection of issues, reducing the risk of deployment failures. By proactively addressing potential errors, you build more reliable and resilient infrastructure setups. In conclusion, prioritizing modularity, consistency, and documentation in HCL projects is essential for success. Modular designs foster reusability, while consistent naming and formatting improve readability. Comprehensive documentation ensures clarity for teams and future maintenance. Adopting tools for automated formatting and validation streamlines workflows and reduces manual effort. By applying these best practices, you create scalable, maintainable, and collaborative code that adapts to evolving infrastructure needs. Remember, the goal is to build configurations that are not only functional, but but also easy to understand and extend. Thank you for your attention. Debugging is the process of identifying and correcting errors or issues within a script to ensure it functions as intended. In the context of script development, debugging plays a critical role in maintaining the integrity and functionality of the code. By addressing errors early in the development cycle, developers can prevent small issues from escalating into larger, more complex problems that are harder to resolve. The primary objectives of this discussion are to enhance the reliability of HCL scripts by minimizing errors and to improve their performance through systematic error resolution. This approach not only saves time, but also ensures that the final script operates efficiently and meets the required specifications. When working with HCL scripts, several common issues can arise. Syntax errors occur when the code violates the language's rules, such as missing semicolons or using incorrect variable names. Logical errors are more subtle and involve flaws in the program's logic, such as incorrect conditionals or loops that do not behave as expected. Runtime errors happen during execution and may include issues like null references or invalid data types that cause the script to crash. Environmental issues are often related to external factors, such as missing dependencies or configuration mismatches that prevent the script from running properly. Understanding these categories helps developers systematically diagnose and address problems in their HCL scripts. HCL provides a variety of tools to assist with debugging. The built-in HCL debugger allows developers to execute scripts step by step, pausing at specific points to inspect the state of the program. Logging mechanisms, such as the HCL log commands, enable developers to record detailed information about the script's execution, which can be invaluable for tracking down issues. Print statements are a straightforward way to display variable values or execution flow at specific points in the code. Additionally, integrated development environments (IDEs) offer advanced features like syntax highlighting, code navigation, and debugging interfaces that streamline the process of identifying and resolving errors. These tools work together to create a robust debugging workflow. Effective debugging requires a structured approach. One key technique is using breakpoints to pause the script at critical points, allowing developers to examine the current state of variables and the program's flow. Inspecting variable values at these points helps determine if the data is as expected. Tracing the execution flow involves following the script's path to identify where it deviates from the intended logic. Evaluating expressions during runtime enables developers to test conditions or calculate values on the fly, which can reveal hidden issues. Combining these techniques provides a comprehensive view of the script's behavior and helps pinpoint the root cause of errors. Troubleshooting HCL scripts involves a methodical process. The first step is to reproduce the issue systematically by recreating the conditions under which the error occurs. This helps ensure that the problem is understood and can be consistently tested. Next, isolating the problematic section of code involves narrowing down the affected area, often by commenting out parts of the script or using debugging tools. Checking HCL documentation for known issues or best practices can provide insights into common pitfalls and solutions. Finally, using version control to compare script changes allows developers to identify when and where an error was introduced, making it easier to roll back or fix the problem. Adopting best practices significantly improves the debugging process. Writing modular and well-documented code ensures that each part of the script has a clear purpose, making it easier to test and debug. Implementing unit testing for individual components verifies that each part functions correctly in isolation, reducing the likelihood of errors. Maintaining a clean and organized script structure, such as using consistent indentation and meaningful variable names, enhances readability and simplifies troubleshooting. Regularly reviewing logs for early error detection helps catch issues before they escalate, ensuring the script remains stable and efficient. To illustrate these concepts, let's examine a few case studies. In one example, a syntax error in a configuration script was resolved by identifying a missing semicolon that caused the script to fail during parsing. Another case involved a runtime error caused by invalid input, which was addressed by adding validation checks to handle unexpected data types. A third example focused on optimizing performance by profiling the script to identify inefficient loops and replacing them with more efficient alternatives. These examples demonstrate how debugging techniques can be applied to real-world scenarios to improve script reliability and efficiency. In conclusion, debugging is an essential practice for creating robust and error-free HCL scripts. By combining the available tools, techniques, and best practices, developers can efficiently identify and resolve issues. The key to successful debugging lies in understanding the script's behavior, systematically troubleshooting problems, and continuously refining the code. As with any skill, mastering debugging requires practice and a commitment to learning. By applying these principles, developers can enhance their ability to create high-quality HCL scripts that perform reliably in real-world environments. Version control is a fundamental practice in software development that allows teams to manage changes to code over time. It acts as a historical record, enabling developers to track modifications, revert to previous versions if needed, and collaborate effectively on the same code base. This system is especially vital in team environments where multiple individuals work on the same project, as it prevents conflicts and ensures that every change is documented and accountable. Without version control, managing code updates would be chaotic, leading to errors, lost work, and difficulties in maintaining a stable product. In HCL projects, version control plays a crucial role in maintaining consistency across development teams. It ensures that all team members are working with the same code base, reducing the risk of incompatible changes. When issues arise, version control allows for easy debugging and rollback of faulty updates, minimizing downtime and preserving the integrity of the application. Additionally, it supports parallel development, where different team members can work on separate features or fixes simultaneously. This capability streamlines the integration of new features and accelerates the overall development cycle. Git is the primary tool used for version control in HCL projects, offering a robust and flexible system for managing code changes. It integrates seamlessly with HCL platforms such as HCL Domino and HCL Notes, allowing developers to store, retrieve, and manage code efficiently. In addition to Git, repositories like GitHub and GitLab serve as central hubs for code storage, enabling teams to collaborate, share code, and track progress. These platforms provide features like issue tracking code reviews, and continuous integration, which further enhance the development workflow. The basic workflow for HCL version control begins with cloning a repository to a local machine, which creates a working copy of the code. Developers then create branches for new features or bug fixes, isolating their changes from the main code base. Once the work is complete, they commit their changes with descriptive messages that explain the purpose of each update. These changes are then pushed to a remote repository, making them available to the team. Finally, branches are merged into the main code base through pull requests, ensuring that all changes are reviewed and integrated systematically. Collaboration in HCL projects thrives on best practices that promote efficiency and quality. Regularly pulling updates from the main branch ensures that developers are working with the latest code, reducing the likelihood of conflicts. Code reviews are essential for maintaining high standards, as they allow team members to evaluate changes before they are merged. Direct commits to main branches should be avoided to prevent instability, and all changes should be documented thoroughly in commit messages and pull requests. This transparency fosters better communication and makes it easier to trace the evolution of the code. Despite its benefits, version control can present challenges. Merge conflicts occur when multiple developers modify the same part of the code, requiring manual resolution or the use of merge tools to reconcile differences. Version mismatches can be mitigated by enforcing strict branching strategies, such as Git flow, which defines clear rules for feature development and releases. Access control is another critical aspect, ensuring that only authorized individuals can make changes to the code. Role-based permissions help maintain security and prevent unauthorized modifications. In conclusion, version control is an essential component of efficient HCL development, providing the structure and tools needed for collaboration and stability. By following structured workflows and fostering clear communication, teams can ensure that their code remains scalable, maintainable, and reliable. Mastering these practices not only enhances productivity, but also builds a foundation for long-term project success. As HCL projects grow in complexity, a strong grasp of version control becomes increasingly vital for delivering high-quality software. HCL2 represents the latest evolution of the HashiCorp configuration language, designed to address the growing complexities of modern infrastructure management. This version introduces a more intuitive syntax that enhances readability and maintainability, making it easier for developers and DevOps engineers to write and understand code. Performance improvements ensure that configurations execute more efficiently, reducing the time required for planning and applying changes. Modularity is a core focus, allowing users to break down large systems into reusable components, which streamlines collaboration and maintenance. By aligning with modern DevOps practices, HCL2 empowers teams to automate workflows, integrate with cloud-native environments, and adapt to dynamic infrastructure needs. This shift not only simplifies the development process, but also strengthens the reliability and scalability of infrastructure as code solutions. One of the most significant advancements in HCL2 is its enhanced syntax, which prioritizes clarity and reduces ambiguity in configuration files. This makes it easier to identify and fix issues during development. The language now supports first-class expressions, enabling dynamic values that can be computed at runtime, which is crucial for complex and evolving infrastructure setups. The improved module system allows for more structured and scalable code organization, with better encapsulation and dependency management. This means developers can create reusable modules that are easier to test and maintain. Additionally, HCL2 introduces more robust error handling and validation mechanisms, which help catch issues early in the development cycle. These features collectively reduce the risk of configuration errors and improve the overall reliability of infrastructure deployments. HCL2 is designed to work seamlessly with existing HCL1X configurations, ensuring a smooth transition for users who have invested in older projects. Most of the syntax from HCL1X remains valid, allowing teams to gradually adopt the new version without a complete rewrite. However, certain legacy constructs, such as the count and for-each syntax, have been deprecated in favor of more flexible and expressive alternatives. These changes are aimed at improving consistency and reducing the potential for errors. To assist with the migration process, HashiCorp provides tools that automate the conversion of configurations, making it easier to update code bases. Additionally, A compatibility mode is available for projects that require a phased transition, allowing users to run HCL2 code alongside older versions while they adapt to the new features. Migrating to HCL2 requires a strategic approach to ensure minimal disruption to existing workflows. The HCL2 toolchain offers automated migration capabilities, which can handle many of the common syntax changes and deprecations. However, it is essential to review deprecated features and replace them with the corresponding HCL2 equivalents, such as using the for expression instead of count. Testing configurations in isolation is a critical step, as it allows teams to verify that changes do not introduce unexpected behavior. This process should be followed by thorough validation in staging environments before deploying to production. Leveraging the extensive community resources and official documentation can provide valuable guidance, especially for teams encountering specific challenges during the migration. By following these strategies, organizations can ensure a more efficient and error-free transition to HCL2. While HCL2 offers numerous benefits, the migration process can present several challenges. One of the primary issues is the breaking changes in syntax and module interactions, which may require significant adjustments to existing configurations. Third-party tools and plugins that were designed for HCL 1X may not be fully compatible, necessitating updates or alternatives. This highlights the importance of thorough testing during migration, as even minor changes can have cascading effects on infrastructure. Additionally, developers who are unfamiliar with HCL2 may face a learning curve, particularly when working with new features like first-class expressions or the updated module system. Addressing these challenges requires a combination of technical expertise, careful planning, and ongoing support from both the community and HashiCorp. HCL2 is particularly well suited for scenarios that demand dynamic and scalable infrastructure solutions. For complex deployments, the ability to use dynamic values and expressions allows configurations to adapt to changing requirements without manual intervention. Large-scale projects benefit from the improved module system, which enables better organization and reuse of code across different environments. Integration with modern CI/CD pipelines is another key advantage, as HCL2's structured approach facilitates automated testing, deployment, and monitoring. Furthermore, its support for cross-cloud and multi-environment management makes it an ideal choice for organizations operating in hybrid or multi-cloud environments. These capabilities ensure that HCL2 can handle the demands of today's rapidly evolving infrastructure landscapes. In summary, HCL2 delivers substantial improvements over its predecessor, making it a powerful tool for modern infrastructure management. The compatibility features ensure that existing projects can transition smoothly without significant disruption. By adopting HCL2, teams can enhance their productivity, reduce the risk of errors, and achieve more efficient infrastructure workflows. However, successful migration requires a commitment to continuous learning and thorough testing. As organizations embrace these advancements, they will be better equipped to meet the challenges of cloud-native environments and DevOps practices. The future of infrastructure as code is here, and HCL2 is leading the way. Custom data sources and resources in HCL programming language serve as essential components that allow developers to extend the functionality of their applications beyond the default capabilities. By defining custom data sources, you can integrate external or internal data into your HCL workflows, enabling the system to pull information from various locations, such as databases, APIs, or configuration files. This integration not only enhances the flexibility of your applications, but also allows them to scale effectively as data needs evolve. For advanced HCL programming, mastering these elements is crucial because they provide the foundation for building complex, dynamic systems that can adapt to changing requirements. Understanding how to implement and manage these components ensures that your code remains efficient and future-proof. Custom data sources act as bridges between your HCL applications and external systems. For instance, an API can be a custom data source that fetches real-time data from a web service, while a database might serve as a source for structured information. Configuration files, on the other hand, can provide settings or parameters that influence how your application behaves. These data sources are not static. They enable dynamic data retrieval during runtime, meaning your application can access and process information as it is needed. This dynamic approach improves responsiveness and reduces the overhead of loading all data at once. By leveraging custom data sources, developers can create applications that are more adaptable and capable of handling diverse data environments. Custom resources in HCL are user-defined components designed to perform specific tasks that are not covered by the built-in features of the language. These resources can take many forms, such as custom modules that encapsulate complex logic, data structures tailored to specific needs, or service wrappers that simplify interactions with external systems. By creating custom resources, developers can break down their code into reusable, manageable parts, which significantly improves code reusability and maintainability. This modular approach allows for easier debugging, updates, and collaboration among team members. Ultimately, custom resources empower developers to build more efficient and scalable applications by focusing on creating solutions that align precisely with their project requirements. Creating custom data sources involves several key steps that ensure they function effectively within an HCL environment. The first step is to define the data structure that the custom data source will handle, which includes specifying the format and types of data it will access. Next, you must implement the access logic, which involves writing code that interacts with the external system, such as querying a database or calling an API. HCL provides built-in APIs that simplify this process, allowing developers to integrate these data sources seamlessly. Finally, validating data integrity and implementing error handling are critical to ensure that the data retrieved is accurate and that the system can gracefully handle any issues that arise during runtime. These steps collectively ensure that your custom data sources are reliable and performant. When creating custom resources, the process begins with designing the resource logic, which involves determining how the resource will interact with the rest of the system and what functionality it will provide. Once the logic is defined, the next step is to register the resource with the HCL runtime environment, making it available for use in your applications. HCL's modular architecture supports this by allowing resources to be encapsulated and reused across different projects. Testing the interactions between these custom resources and existing systems is equally important to ensure compatibility and reliability. This testing phase helps identify any potential conflicts or performance issues, ensuring that the custom resources enhance rather than disrupt the overall system. Adhering to best practices when working with custom data sources is essential for maintaining security and efficiency. One of the primary concerns is ensuring secure data access and authentication, which involves implementing measures such as API keys, OAuth, or encrypted connections to protect sensitive information. Maintaining version control for data source configurations helps track changes over time and revert to previous versions if needed. Additionally, documenting APIs and dependencies clearly is crucial for collaboration and future maintenance. These practices not only prevent potential issues, but also make it easier for teams to understand and manage the data sources throughout the application's lifecycle. For custom resources, following HCL's Resource Lifecycle Management guidelines ensures that they are created, deployed, and maintained efficiently. This includes planning for how the resource will be initialized, used, and eventually decommissioned. Avoiding hard-coding sensitive information, such as passwords or API keys, into the resource code is another critical best practice, as it reduces the risk of exposure and makes the code more flexible. Instead, these values should be sourced from external configuration files or environment variables. A modular design further enhances the resource's adaptability, allowing developers to update or debug specific components without affecting the entire system. This approach leads to more robust and maintainable code. To illustrate the practical application of custom data sources and resources, consider a scenario where a third-party API is integrated as a custom data source. For example, a weather application might use a custom data source to fetch real-time weather data from an external service, enabling dynamic updates without requiring manual input. Another example is a custom resource designed for cloud storage access, which could encapsulate the logic for uploading and retrieving files from a service like Amazon S3. These examples highlight how custom data sources and resources enable scalable application development by allowing developers to build solutions that adapt to complex real-world requirements. By leveraging these tools, teams can create applications that are both powerful and efficient. In summary, custom data sources and resources are vital tools that expand the capabilities of the HCL programming language, They allow developers to create flexible, scalable, and efficient applications by integrating diverse data and functionality. Proper implementation of these elements ensures that systems can handle evolving demands while maintaining reliability. By following best practices and applying these concepts thoughtfully, developers can build robust and maintainable code that meets the challenges of modern software development. Embracing these techniques will empower you to create more advanced and effective HCL applications. Security is a cornerstone of any programming language, and HCL is no exception. In HCL, ensuring security isn't just a technical requirement. It's a responsibility to protect data, systems, and users from potential harm. The three key security goals, confidentiality, integrity, and availability, form the foundation of secure development. Confidentiality ensures that sensitive information is accessible only to authorized users. Integrity guarantees that data remains accurate and unaltered throughout its life cycle. Availability ensures that systems and data are accessible when needed. However, these goals face challenges from common security threats such as unauthorized access, data breaches, and malicious attacks. Understanding these threats is the first step in building resilient HCL applications. Input validation and sanitization are critical steps in preventing injection attacks, which can exploit vulnerabilities in user inputs. In HCL, developers must validate all inputs, whether from users, external systems, or APIs, to ensure they conform to expected formats and constraints. HCL provides built-in validation functions that can help check data types, ranges, and patterns. However, validation alone isn't enough. Sanitization is equally important. This involves cleaning inputs to remove or neutralize any potentially harmful content, such as special characters or malicious code. By combining validation and sanitization, developers can significantly reduce the risk of attacks like SQL injection or command injection, which can compromise the integrity of HCL applications. Secure data handling in HCL requires a proactive approach to protecting sensitive information. Encryption is a fundamental technique, ensuring that data remains unreadable to unauthorized parties, both when stored and during transmission. Developers should use strong encryption protocols, such as AES for data at rest and TLS for data in transit. Hard-coding credentials, such as database passwords or API keys, in HCL scripts is a major security risk. Instead, developers should leverage secure storage mechanisms like environment variables, encrypted configuration files, or dedicated secret management tools. By adopting these practices, HCL applications can safeguard critical data from exposure and misuse. Authentication and authorization are essential for controlling access to HCL applications and resources. Robust authentication mechanisms, such as multi-factor authentication or biometric verification, ensure that only legitimate users can access the system. HCL offers libraries and frameworks to manage secure token generation, storage, and validation, which can be used to implement secure session management. Once authenticated, users must be granted access based on their roles and responsibilities. Role-based access control, RBAC, is a powerful strategy here, allowing developers to define permissions hierarchically. This ensures that users have the minimum necessary access to perform their tasks, reducing the risk of accidental or intentional misuse. Secure API integration in HCL demands careful attention to both incoming and outgoing requests. Every API call should be validated to ensure it adheres to expected parameters, headers, and payloads. This helps prevent malicious or malformed requests from exploiting vulnerabilities. Using HTTPS for all API communications is non-negotiable, as it encrypts data in transit and prevents eavesdropping or tampering. Additionally, developers should implement the principle of least privilege by limiting API permissions to the bare minimum required for each service or user. This reduces the attack surface and ensures that even if one API is compromised, the damage is contained. Despite best practices, HCL applications are still vulnerable to specific threats. SQL injection remains a persistent risk, as attackers can inject malicious queries through untrusted inputs to manipulate databases. Cross-site scripting XSS is another concern, particularly in HCL templates where user-generated content might be rendered without proper filtering, allowing attackers to inject malicious scripts. Insecure dependency management is also a common issue. Using outdated or untrusted libraries can introduce vulnerabilities that compromise the entire application. Addressing these threats requires vigilance in code review, dependency updates, and secure coding practices. Adhering to best practices is the best defense against security risks in HCL. Regularly updating HCL libraries and dependencies ensures that known vulnerabilities are patched and that the code base remains resilient to emerging threats. Conducting thorough code reviews helps identify security flaws that automated tools might miss, fostering a culture of accountability and collaboration. Static analysis tools can also be integrated into the development workflow to detect potential vulnerabilities early. By combining these strategies, developers can create HCL applications that are not only functional, but also secure and maintainable over time. In conclusion, security is not an afterthought, but a fundamental aspect of HCL development. By prioritizing input validation, data protection, and access control, developers can build applications that are both robust and trustworthy. Staying informed about emerging threats and evolving mitigation strategies is equally important, as the security landscape is constantly changing. With a commitment to best practices and continuous learning, HCL developers can ensure their applications remain secure in an increasingly complex digital world. Performance optimization in HCL programming refers to the process of refining code to ensure it runs efficiently, uses resources wisely, and meets the demands of complex applications. In the context of HCL, which is often used for enterprise-level scripting and automation, efficient code is critical for scalability. When applications grow, poorly optimized code can lead to excessive memory consumption, slow execution, and difficulty in managing large data sets. The key areas to focus on include memory usage, which involves minimizing unnecessary allocations and ensuring proper garbage collection, execution speed, which requires reducing redundant operations and optimizing algorithms, and code efficiency, which means writing clean, maintainable scripts that avoid unnecessary complexity. By prioritizing these areas, developers can create HCL scripts that perform reliably under heavy workloads. To optimize HCL code effectively, start by avoiding redundant computations. For example, if a calculation is repeated multiple times in a script, store the result in a variable instead of recalculating it. This reduces processing overhead and improves readability. Next, minimize nested loops and excessive conditional checks. Deeply nested loops can drastically increase runtime, especially with large data sets. So consider replacing them with iterative data structures or flattening logic where possible. Finally, leverage HCL's built-in functions and modules. These are often written in lower-level languages and are highly optimized for performance. Using them instead of custom implementations ensures faster execution and reduces the risk of errors. By following these practices, developers can create cleaner, faster, and more maintainable HCL scripts. One common pitfall in HCL is the overuse of global variables. While convenient, global variables can lead to memory bloat and make code harder to debug, as their values can be modified anywhere in the script. Another issue is inefficient string concatenation in loops. For instance, appending strings repeatedly in a loop can cause significant performance degradation, as each operation creates a new string object. Instead, use a list to collect strings and join them at the end. Lastly, a lack of proper error handling can introduce runtime overhead. Unchecked exceptions or unhandled errors force the script to crash or behave unpredictably, which can be mitigated by implementing robust try-catch blocks and validating inputs. Addressing these pitfalls ensures more stable and efficient HCL scripts. Profiling HCL code is essential for identifying performance bottlenecks. HCL provides built-in tools that allow developers to measure execution time, track memory usage, and pinpoint slow functions. For example, the profiling module can generate detailed reports on which parts of the script consume the most resources. In addition, implementing logging mechanisms helps track how long specific operations take and how they affect system resources. Developers can also use third-party analyzers to validate syntax and detect potential inefficiencies, such as unused variables or suboptimal loops. Combining these techniques enables a comprehensive approach to optimizing HCL scripts, ensuring they run smoothly even under demanding conditions. Let's examine a real-world example of optimizing an HCL script. A previous version of a script processing large configuration files took over 10 seconds to complete. But after refactoring, the execution time was reduced by 40%. The key strategy was replacing nested loops with iterative data structures like arrays or hashes, which allowed for more efficient traversal of data. For instance, instead of looping through every element in a multidimensional array, the script now uses a single loop with a hash map to access values directly. This change not only improved speed, but also reduced the memory footprint by minimizing temporary object creation. The result was a more scalable solution that handled larger datasets with ease. Advanced optimization strategies in HCL involve leveraging concurrency for parallel processing. By using HCL's built-in support for asynchronous tasks, developers can execute multiple operations simultaneously, which is particularly useful for I/O-bound tasks like file reading or API calls. Another technique is caching frequent computations using memoization, where results of expensive function calls are stored and reused when needed. For example, a function that calculates complex formulas can cache its output for identical inputs, saving processing time. Finally, optimizing data input and output operations is crucial. Techniques such as buffering data, using binary formats, or minimizing disk access can significantly enhance performance. These strategies enable HCL scripts to handle high workloads efficiently. In summary, the key takeaways for performance optimization in HCL are to prioritize clean, modular code. Writing modular scripts makes it easier to identify and improve inefficiencies. Regularly profiling and testing HCL scripts is essential to uncover hidden bottlenecks and measure the impact of optimizations. Finally, applying best practices consistently ensures that scripts remain efficient and scalable as requirements evolve. By combining these approaches, developers can create HCL solutions that are not only functional, but also optimized for performance, reliability, and future growth. CI/CD, which stands for continuous integration and continuous delivery, is a set of practices that automate the software development lifecycle. This approach ensures that every code change is automatically tested and validated, reducing the risk of errors and allowing teams to release updates more frequently and reliably. By integrating with version control systems like Git, teams can manage code changes collaboratively, ensuring that all modifications are tracked, reviewed, and merged efficiently. This automation not only streamlines the development process, but also minimizes the potential for human error, making the entire workflow more predictable and scalable. HCL, or HashiCorp configuration language, plays a crucial role in modern CI/CD pipelines by enabling infrastructure as code. This means that infrastructure configurations, such as cloud resources or server setups, are defined using code rather than manual processes. HCL allows teams to describe their infrastructure in a declarative way, specifying the desired state of their systems. Tools like Terraform and Packer leverage HCL to automate the provisioning and management of infrastructure, making it easier to version control, test, and deploy changes. This integration ensures that infrastructure is treated as code, aligning it with the same practices used for application development. To effectively integrate HCL into CI/CD pipelines, the first step is to write HCL scripts that define infrastructure resources. These scripts act as blueprints for creating and managing environments. Next, CI/CD tools must be configured to trigger HCL validation and execution, often through automated workflows. For example, every code commit could initiate a pipeline that checks the HCL syntax and applies the configuration. Environment variables are essential for handling dynamic values, such as API keys or region settings, ensuring that the same HCL scripts can be reused across different environments. Finally, implementing testing frameworks helps validate HCL configurations, catching issues early and ensuring that infrastructure changes are safe and reliable. Several tools facilitate HCL integration within CI/CD pipelines. Jenkins, for instance, allows teams to automate the building, testing, and deployment of HCL scripts, providing flexibility through its extensive plugin ecosystem. GitLab CI offers deep integration with Git repositories, enabling pipelines to trigger HCL validation and execution as part of a project's workflow. GitHub Actions simplifies this process by using workflows to automate tasks like syntax checks and infrastructure provisioning. Terraform Cloud centralizes HCL execution, providing a platform for monitoring, logging, and managing infrastructure changes across teams. Each tool brings unique capabilities, allowing organizations to choose the best fit for their specific needs. Adhering to best practices when working with HCL and CI/CD is essential for maintaining a robust and scalable infrastructure. Keeping HCL code modular ensures that it is reusable and easier to maintain, as smaller, focused modules can be combined to build complex systems. Version control for HCL files allows teams to track changes, revert to previous states if needed, and collaborate effectively. Validating HCL syntax before pipeline execution prevents errors that could disrupt deployments, while monitoring and logging HCL execution provides visibility into what is happening during infrastructure changes. These practices collectively enhance the reliability and efficiency of the CI/CD process. Integrating HCL into CI/CD pipelines can present challenges, but solutions exist to address them. One common issue is managing complex HCL dependencies, where multiple resources rely on each other. Using dependency management tools helps track and resolve these relationships, ensuring that changes are applied in the correct order. Environment mismatches, where configurations work in one environment but fail in another, can be mitigated by leveraging HCL variables and outputs to customize deployments. Security in pipelines is another concern, as sensitive data like credentials must be protected. Encrypting sensitive HCL data and using secure secret management practices ensures that this information remains confidential and tamper-proof. In conclusion, integrating HCL with CI/CD pipelines transforms infrastructure management into a seamless, automated process. This synergy enhances testing, deployment, and collaboration across teams, enabling faster and more reliable software releases. Prioritizing modularity, validation, and security ensures that HCL configurations remain maintainable and secure over time. As technology evolves, continuous learning and adaptation are critical for staying ahead of challenges and leveraging new capabilities. By embracing these practices, organizations can build resilient, scalable infrastructure that supports their development goals. State management is a fundamental concept in infrastructure as code, ensuring that every change to your configuration is tracked consistently. This is especially important when working with HCL, as it allows teams to maintain a clear and accurate record of what resources exist in the real world. Without proper state management, it's easy to lose track of what has been deployed, leading to inconsistencies and errors. Locking mechanisms complement this by preventing multiple users or processes from making conflicting changes at the same time. This is critical in collaborative environments where multiple team members might be working on the same infrastructure simultaneously. By combining state management with locking, HCL ensures that your workflows remain reliable. Whether you're automating deployments or working in a team setting, in HCL, state management relies on a state file that acts as a central record of your infrastructure. This file maps every resource defined in your HCL configurations to its actual representation in the real world. For example, if you define a virtual machine in your code, the state file keeps track of its unique identifier, its current status, and any associated attributes. As you modify your HCL files, the state file updates automatically to reflect these changes. This ensures that the state file always aligns with the infrastructure you're managing. This dynamic relationship between HCL configurations and the state file is essential for maintaining accuracy, allowing tools to apply changes predictably and avoid unexpected behavior. The state file in HCL is structured to include key components such as resource IDs, attributes, and dependencies. Resource IDs uniquely identify each resource, ensuring that changes can be tracked precisely. Attributes describe the current state of a resource, like its IP address or status. Dependencies define how resources are connected, which is critical for ensuring that operations are executed in the correct order. To support collaboration, HCL allows you to store the state file in remote backends like Amazon S3 or Console. These backends enable teams to share the same state, preventing conflicts and ensuring everyone works with the latest information. Additionally, state versioning allows you to track changes over time, making it easier to roll back to previous states if needed. Locking mechanisms in HCL are designed to prevent multiple users from modifying the same state file simultaneously. When a user initiates an operation, a lock is created to ensure no other user can make changes until the current operation completes. This lock is stored in a file, which acts as a template temporary marker to indicate that the state is in use. Once the operation finishes, the lock is automatically released, allowing others to proceed. This process is essential for maintaining consistency, as overlapping changes could otherwise lead to conflicts or corrupted infrastructure. By enforcing exclusive access during critical operations, locking mechanisms help preserve the integrity of your infrastructure. Concurrency control is a key aspect of managing infrastructure with HCL, ensuring that updates are applied in a way that maintains consistency. Locking plays a central role here, as it guarantees that changes are atomic, either fully applied or not at all. However, if an operation fails unexpectedly, such as a network error or a system crash, the lock might remain in place, blocking further changes. In such cases, manual intervention is required to release the lock. HCL provides a command called Terraform Force Unlock for emergency scenarios, allowing administrators to override the lock and proceed. While this is a powerful tool, it should be used cautiously to avoid introducing conflicts or data corruption. Following best practices for state and locking is essential for maintaining a reliable and secure infrastructure. One of the most important practices is to use remote state backends in team environments. This ensures that all team members access the same state file, reducing the risk of conflicts and inconsistencies. Manually editing state files is strongly discouraged, as it can introduce errors or break the relationship between configurations and the actual infrastructure. Instead, rely on HCL tools to manage changes automatically. Regularly backing up state files is another critical step, as it protects against data loss due to accidental deletions, system failures, or other unforeseen issues. These practices collectively help maintain the integrity and security of your infrastructure. In summary, effective state management and locking mechanisms are vital for ensuring that your HCL workflows operate smoothly and reliably. State management provides a consistent view of your infrastructure, while locking prevents conflicts during collaborative or automated changes. These features work together to maintain the integrity of your resources, whether you're deploying a single resource or managing a complex environment. By adhering to best practices, such as using remote backends, avoiding manual edits, and regularly backing up state files, you can ensure that that your infrastructure remains secure, consistent, and easy to manage over time. Error handling is a fundamental aspect of creating reliable and stable HCL configurations. When working with infrastructure as code, even small mistakes can lead to significant failures during deployment. By implementing proper error handling, we ensure that our configurations can detect and manage issues before they escalate. This not only prevents unexpected crashes, but also makes the development process more predictable. For example, if a resource is missing a required parameter, error handling can flag this early, allowing developers to address it before it causes a deployment failure. This proactive approach saves time and reduces the risk of costly errors in production environments. Understanding the different types of errors in HCL is essential for effective troubleshooting. Syntax errors occur when the HCL code violates the language's structure rules, such as missing brackets or incorrect indentation. These errors are usually caught during the initial parsing phase, making them easier to identify. Runtime errors, on the other hand, happen when the code is executed but encounters invalid operations, like using an undefined variable or referencing a non-existent resource. Validation errors are a bit more nuanced, as they arise when input values fail to meet specified constraints, such as a numeric value being outside an expected range. Recognizing these categories helps in diagnosing issues more efficiently and implementing targeted solutions. HCL provides several built-in validation functions that empower developers to enforce data integrity. The length function allows us to check the size of strings, lists, or maps, ensuring they meet specific criteria. For instance, we can use it to verify that a password input has a minimum length requirement. The type function helps confirm that a variable holds the correct data type, such as a string or a number, which is crucial for preventing type-related errors. The contains function is particularly useful for validating the presence of specific elements within a list or map, such as ensuring a required key exists in a configuration. These functions work together to create a robust validation layer for HCL configurations. Validation blocks in HCL are a powerful tool for defining constraints on input variables, especially in Terraform modules. By specifying rules within a validation block, we can ensure that variables adhere to expected values or formats. For example, a validation block might check that a variable representing a port number falls within the valid range of 1 to 65,535. Another common use case is ensuring that a required variable is not empty, which prevents scenarios where missing inputs lead to undefined behavior. These blocks act as a safeguard, making configurations more resilient and reducing the likelihood of deployment failures due to invalid inputs. Handling errors within HCL expressions requires a strategic approach to ensure code stability. The try function is particularly useful for gracefully managing potential failures in expressions. For instance, if a variable might be undefined, using tryvar value default allows the code to fall back to a default value instead of crashing. Combining try with the error function enables developers to raise custom error messages when specific conditions are not met, providing clearer feedback for debugging. This combination of error handling techniques makes HCL expressions more robust, especially in complex configurations where dependencies and variables can vary widely. Adopting best practices for error handling is critical for maintaining high-quality HCL configurations. Proactive validation of inputs is the first line of defense against downstream failures. By checking variables and parameters early in the process, we can prevent issues from propagating through the system. Descriptive error messages are equally important, as they provide actionable insights for troubleshooting. For example, instead of a generic invalid input message specifying the region must be one of us East 1, us West 2, or EU West 1, helps users quickly resolve the problem. Finally, testing configurations with edge cases, such as empty inputs or extreme values, ensures that the system remains resilient under unexpected conditions. Real-world scenarios often require specific validation rules to ensure consistency and correctness. In network configurations, validating IP addresses or CIDR ranges is essential to prevent misconfigurations that could compromise security or connectivity. Similarly, enforcing naming conventions for resources like virtual machines or storage buckets helps maintain a clean and organized infrastructure. Another common requirement is checking for the presence of required variables in modules, which ensures that all dependencies are explicitly defined. These validation scenarios highlight how HCL's error handling capabilities can be tailored to meet the unique needs of different use cases. Effective debugging is a crucial skill for any HCL developer. The Terraform Plan command is an invaluable tool for identifying potential issues before they affect the actual infrastructure. It provides a preview of changes, highlighting errors or warnings that need attention. The Terraform Apply command with the target flag allows for testing specific resources without applying changes to the entire configuration, which is useful for isolating problems. Additionally, reviewing logs and error messages generated during execution helps pinpoint the root cause of failures. These techniques, when used together, create a comprehensive approach to debugging and improving configuration reliability. A real-world example illustrates the impact of effective error handling. Imagine a module that provisions a cloud instance, but fails due to an invalid input, such as an incorrect region or an unsupported instance type. Without validation, this could lead to a failed deployment and wasted time. By implementing validation blocks and custom error messages, the module can detect the invalid input early and provide clear guidance to the user. This not only reduces deployment failures, but also enhances the user experience by making it easier to correct mistakes. The result is a more stable and user-friendly infrastructure setup process. In conclusion, error handling and validation are indispensable components of any HCL workflow. They provide the framework for building resilient configurations that can withstand unexpected challenges. By leveraging built-in functions like length, type, and contains, developers can enforce data integrity and prevent common mistakes. Following best practices such as proactive validation and descriptive error messages further enhances the reliability of HCL configurations. Ultimately, prioritizing error handling ensures that infrastructure as code remains predictable, maintainable, and scalable in dynamic environments. Hello. Today, we will explore the critical process of testing HCL configurations. HCL, or HashiCorp Configuration Language, is a domain-specific language used to define infrastructure as code. It allows developers and DevOps engineers to describe cloud resources, configurations, and dependencies in a structured and human-readable format. By using HCL, teams can manage infrastructure in a consistent and repeatable manner, which is essential for modern cloud environments. Testing these configurations is vital because even a small mistake can lead to significant deployment errors, security vulnerabilities, or resource misconfigurations. The primary objectives of testing HCL configurations include validating that the code meets specified requirements, detecting errors early in the development cycle, and ensuring consistency across different environments. This process helps prevent costly failures and ensures that infrastructure is both reliable and secure. To effectively test HCL configurations, we rely on a variety of tools. Terraform, the core tool for HCL, provides built-in commands like Terraform Validate and Terraform Plan. The Validate command checks for syntax errors and ensures that the configuration is well formed, while the Plan command simulates the execution of the configuration to identify potential issues. In addition to Terraform, static analysis tools such as TF-Lint and Terrascan are invaluable. TF-Lint enforces best practices and checks for syntax issues, while Terrascan scans configurations for compliance with security policies. For more granular testing, unit testing frameworks like Inspec and BATS can be used to validate specific scenarios, such as whether a resource is created with the correct parameters. Finally, mock environments allow us to perform end-to-end testing by simulating real-world conditions without affecting production systems. These tools work together to provide a comprehensive testing strategy. Adopting best practices is essential for effective testing of HCL configurations. One key practice is modularizing configurations, which involves breaking down complex setups into smaller, reusable modules. This approach makes it easier to isolate and test individual components, reducing the risk of cascading failures. Version control is another critical practice, as it enables teams to track changes, collaborate efficiently, and roll back to previous versions if issues arise. Integrating testing into CI/CD pipelines ensures that every code change is automatically validated, which accelerates feedback and reduces manual effort. Finally, documenting test cases and their expected outcomes is crucial for reproducibility. Clear documentation helps new team members understand the testing process and ensures that tests remain relevant as configurations evolve. These practices collectively enhance the reliability and maintainability of HCL-based infrastructure. Testing HCL configurations involves addressing several common scenarios. First, validating resource dependencies is essential because infrastructure components often rely on each other. For example, a virtual machine might depend on a subnet and a security group, and ensuring these relationships are correctly defined prevents deployment failures. Second, testing variable inputs helps identify edge cases, such as invalid data types or missing parameters, which could cause unexpected behavior. Third, checking output values ensures that the results of a configuration match expectations, such as verifying that a public IP address is assigned correctly. Finally, simulating environment-specific scenarios, like deploying to different regions or cloud providers, ensures that configurations are adaptable and resilient. These scenarios cover the most critical aspects of HCL testing and help build robust infrastructure. When issues arise during testing, a systematic approach to troubleshooting is necessary. Error messages from Terraform commands often provide clues about the root cause, such as a missing resource or incorrect parameter. Using the Terraform show command allows us to inspect the generated plan and state files, offering visibility into how Terraform interprets the configuration, enabling debug logging, typically through environment variables like TFLOG, provides detailed insights into the execution process, which is invaluable for diagnosing complex issues. Once a problem is identified, fixing it and rerunning tests iteratively ensures that the solution addresses the root cause and does not introduce new issues. This cycle of testing, debugging, and retesting is fundamental to maintaining high-quality infrastructure. In conclusion, testing HCL configurations is a cornerstone of reliable infrastructure management. By combining automated tools, best practices, and scenario-based testing, teams can ensure that their configurations are accurate, secure, and scalable. Automated testing reduces the risk of human error and accelerates the deployment process, while scenario-based testing prepares teams for real-world challenges. Continuous testing within CI/CD pipelines further enhances confidence in infrastructure changes. Applying these techniques to real-world projects not only improves the quality of deployments, but also fosters a culture of continuous improvement. As infrastructure becomes increasingly complex, a disciplined approach to testing remains essential for success. Conditionals are fundamental to programming in HCL, as they allow scripts to make decisions based on specific criteria. Understanding how to use them effectively is crucial for writing dynamic and responsive code. While basic FL structures handle straightforward decisions, advanced conditionals enable more sophisticated logic that can adapt to varying scenarios. This is particularly important in HCL, where configurations often need to account for multiple variables and dependencies. Ensuring that these expressions are clear and easy to maintain is essential, as complex logic can quickly become difficult to debug or modify without proper structure. By prioritizing readability, developers can create scripts that are not only functional, but also easier for others to understand and collaborate on. Nested conditional expressions allow for multi-tiered decision-making by embedding if statements within one another. This approach is useful when a series of conditions must be evaluated sequentially, such as checking for different user roles or system states. For example, a script might first check if a user is authenticated, then determine their access level, and finally execute specific actions based on that. However, excessive nesting can lead to what is known as the pyramid of doom, where the code becomes visually complex and hard to follow. To avoid this, it is advisable to limit the depth of nesting, use helper functions, or restructure logic using alternative constructs. By keeping the flow of conditions simple and linear, developers can maintain clarity and reduce the risk of errors in their scripts. The ternary operator provides a concise way to express simple conditional assignments in HCL. Its syntax is straightforward, with a condition followed by a question mark, then the value to return if the condition is true, and a colon for the false case. This operator is particularly useful for assigning values based on a single check, such as determining a status label or a default configuration. For instance, a script might use a ternary to set a variable to high if a value exceeds a threshold, or low otherwise. While the ternary operator simplifies code, it should be used judiciously to avoid making expressions overly compact. Balancing brevity with readability ensures that the logic remains clear, even for those who may not be familiar with the operator. Logical operators such as and, or, and not are essential for combining multiple conditions in HCL. These operators allow scripts to evaluate complex scenarios by checking whether multiple criteria are met simultaneously. For example, a condition might require both a specific region and a budget threshold to be satisfied before executing an action. Understanding the precedence of these operators is critical, as it determines the order in which conditions are evaluated. Not has the highest precedence, followed by and then or. However, parentheses can override this default order, ensuring that expressions are evaluated exactly as intended. Proper use of logical operators and parentheses helps prevent logical errors and makes the intent of the code more explicit. In real-world applications like Terraform, combining conditions is vital for dynamic resource allocation. For example, a script might check if a region is set to a specific value and if a budget constraint is met before provisioning resources. This approach allows configurations to adapt to different environments or user inputs without requiring manual changes. By leveraging compound conditions, developers can create flexible and scalable infrastructure setups. Another example could involve checking for the presence of certain variables or the outcome of previous steps to determine the next course of action. These practical uses demonstrate how advanced conditionals empower HCL scripts to handle complex scenarios efficiently. Common pitfalls in conditional expressions often arise from oversight or misunderstanding of syntax. One frequent mistake is omitting parentheses in complex expressions, which can lead to unexpected evaluation orders. For instance, a condition that relies on a specific sequence of checks might fail if parentheses are missing. Another issue is using the assignment operator instead of the equality operator, which can introduce subtle bugs that are difficult to trace. Additionally, failing to account for null or undefined variables can cause runtime errors, especially in dynamic configurations. Addressing these issues requires careful attention to detail, thorough testing, and the use of tools that highlight potential syntax or logical errors. Adopting best practices for conditionals enhances the reliability and maintainability of HCL scripts. Breaking down long conditions into smaller, reusable variables improves readability and makes the logic easier to debug. For example, a complex condition might be split into separate variables that describe individual checks, allowing the script to reference them by name. Documenting these conditions with comments ensures that future developers understand the intent behind each check. Furthermore, testing edge cases such as unexpected values or missing variables helps identify potential issues before they affect real-world scenarios. By following these practices, developers can create robust and adaptable configurations that stand the test of time. Mastering advanced conditionals is a key step in becoming proficient with HCL, as it enables the creation of more dynamic and efficient scripts. The ability to structure complex logic clearly and maintainably is invaluable, especially in environments where configurations must adapt to changing requirements. Prioritizing clarity over brevity ensures that scripts remain accessible to others and easier to modify over time. Finally, consistent practice with real-world scenarios reinforces these concepts, helping developers apply theoretical knowledge to practical challenges. By focusing on these principles, learners can unlock the full potential of HCL and build more reliable, scalable solutions. Complex data structures are advanced tools that help organize and manage large volumes of data in a structured way. These structures are essential because they allow programmers to model real-world problems more effectively. For instance, when dealing with data that has relationships or hierarchies, simple variables or basic arrays fall short. Complex data structures like arrays, linked lists, trees, graphs, and hash tables provide the flexibility and efficiency needed to handle such scenarios. By using these tools, developers can optimize operations like searching, sorting, and data retrieval, which are critical for building scalable applications. Understanding these structures is foundational for anyone looking to master the HCL programming language. In HCL, arrays are the most basic form of complex data structures, allowing you to store multiple values of the same type in a single variable. A single-dimensional array is like a list, where each element is accessed using an index. For example, if you have an array called numbers, you can access the third element using numbers too. multi-dimensional arrays, such as two-dimensional or three-dimensional arrays, are used to represent grids or matrices. These structures require careful memory allocation, as each element must be stored in contiguous memory locations. When declaring an array in HCL, you specify the size and data type, like numbers equals 5 integer. Accessing elements involves using multiple indices, such as matrix 12. These structures are widely used in applications like image processing and scientific computations. Linked lists are another critical data structure in HCL, where each element, called a node, contains data and a pointer to the next node in the sequence. This dynamic nature allows for efficient insertion and deletion of elements compared to arrays. Singly linked lists have nodes that point only to the next node, while doubly linked lists have nodes that point to both the next and previous nodes, enabling bidirectional traversal. Dynamic memory allocation in HCL is essential for managing linked lists, as it allows the program to allocate and free memory as needed. For example, using functions like allocate and release in HCL ensures that memory is efficiently used and prevents leaks. This flexibility makes linked lists ideal for applications requiring frequent modifications to data. Trees are hierarchical data structures that consist of nodes connected by edges, with a single root node at the top. Each node can have multiple child nodes, forming a branching structure. Binary trees, a common type, restrict each node to having at most 2 children. Traversal methods like inorder and preorder help navigate the tree, allowing operations such as searching and sorting. In HCL, trees are used extensively in file systems to represent directory structures, and in databases for efficient data retrieval. For example, a binary search tree can quickly locate data by comparing values, making it a powerful tool for organizing and accessing information. Understanding trees is crucial for developing applications that require hierarchical data management. Graphs are used to model relationships between entities, consisting of vertices connected by edges. They can represent both directed and undirected connections, making them versatile for various applications. Directed graphs, or digraphs, have edges with a specific direction, while undirected graphs have bidirectional connections. In HCL, adjacency lists and matrices are common ways to represent graphs. an adjacency list stores each vertex's neighbors, while a matrix uses a grid to indicate connections. These representations are vital for tasks like network analysis, social media connections, and route optimization. By leveraging graphs, HCL developers can solve complex problems involving interconnected data. To illustrate the practical use of complex data structures in HCL, let's look at a code example. Suppose we want to build a linked list. We would start by defining a node structure with data and a pointer. Then, functions for inserting and deleting nodes would be implemented. For instance, inserting a new node involves adjusting pointers to maintain the list's integrity. Similarly, in a binary tree, operations like adding a node or traversing the tree require careful handling of pointers. Error handling, such as checking for null pointers, is essential to prevent crashes. Memory management is equally important, as improper allocation can lead to leaks. These examples highlight how HCL's syntax and features enable robust implementation of complex structures, while complex data structures offer powerful capabilities. They come with challenges. One common pitfall is memory leaks, which occur when allocated memory is not properly freed, leading to resource exhaustion. Time complexity is another concern, as inefficient algorithms can slow down applications. To mitigate these issues, developers should adopt modular design principles, breaking down problems into reusable components. Code reusability reduces redundancy and improves maintainability. Testing and debugging are also critical, as they help identify and fix issues early. By following best practices, HCL programmers can create efficient, reliable, and scalable solutions that meet real-world demands. In summary, complex data structures like arrays, linked lists, trees, and graphs form the backbone of efficient programming in HCL. They enable the organization and manipulation of data in ways that simple structures cannot. Whether you are building a file system, optimizing a database, or analyzing networks, mastering these tools is essential. As you continue your journey with HCL, remember to apply these concepts to real-world scenarios. Practice is key to understanding their nuances and leveraging their full potential. By doing so, you will become adept at solving complex problems and developing innovative applications Functions are reusable code blocks that perform specific tasks, which means you can write a piece of code once and use it multiple times throughout your program. This not only saves time, but also reduces errors because you're working with proven code. Custom functions allow developers to encapsulate logic, which means you can group related operations into a single unit. This approach makes your code more modular, so you can manage and update parts of your program independently. User-defined functions are essential for enhancing code readability and maintainability. When you give a function a clear name and purpose, it becomes easier for others and yourself to understand what the code does. HCL supports defining functions with parameters and return values, which means you can pass data into a function and get results back, making your code dynamic and versatile. To declare a custom function in HCL, you use the function keyword followed by the name of the function and a set of parentheses that may contain parameters. The syntax is straightforward. Function name parameters, where the curly braces enclose the code that the function executes. Functions can be nested, meaning you can define one function inside another, which can help organize complex logic. They can also be defined in separate modules, which allows you to structure your code into logical sections. For example, a function called add that takes two parameters a and b and returns their sum would look like function adda. B, return a plus b. This simple example shows how HCL functions can handle basic operations while remaining easy to read and modify. Parameters are the variables listed in a function's definition, acting as placeholders for the values that will be passed to the function when it is called. These values, known as arguments, are the actual data provided during the function call. HCL supports both positional and named parameters, giving developers flexibility in how they pass data. Positional parameters are matched based on their order, while named parameters allow you to specify which value corresponds to which parameter, making the code more readable. Additionally, HCL allows you to assign default values to parameters, which means if no argument is provided, the function will use the default value instead. This feature increases the function's flexibility and reduces the need for multiple function overloads. Functions in HCL can return a single value using the return statement, which sends the result of the function back to the caller. However, when you need to return multiple values, HCL allows you to use tuples or objects to bundle them together. For instance, a function might return an object containing multiple pieces of data, such as a result and a status message. This approach is particularly useful when you need to convey more information than a single value can hold. The return value is crucial because it allows functions to communicate their outcomes to other parts of the program, enabling further processing or decision-making. An example of this is returning an object with properties like result and status, which can then be used to determine the next steps in your code. Variables declared inside a function have local scope, meaning they are only accessible within that function. This is important because it prevents unintended modifications to variables from other parts of the program. In contrast, global variables are accessible throughout the entire program, which can be convenient, but also risky if not managed carefully. Proper scoping is essential for avoiding naming conflicts, where two variables with the same name might interfere with each other. HCL enforces strict scoping rules for user-defined functions, ensuring that variables are only accessible where they are needed. This practice improves code safety and makes it easier to debug and maintain your programs. User-defined functions can be applied in various scenarios to solve specific problems. For example, a function to calculate factorial would take a number and return the product of all positive integers up to that number, demonstrating how functions can handle mathematical operations. Another example is a function that validates user input, checking if the data meets certain criteria before processing it further. This helps ensure that your program behaves correctly, even with unexpected inputs. Additionally, functions can process and return JSON data, which is common in applications that interact with web services or APIs. By reusing these functions across modules and projects, you can streamline development and reduce redundancy, making your code more efficient and easier to manage. When creating functions, it's important to follow best practices to ensure your code remains clean and manageable. One key principle is the single responsibility principle, which means each function should focus on a single task. This makes functions easier to test, debug, and reuse. Using descriptive names for functions and parameters helps others understand their purpose without needing additional explanations. avoiding side effects by minimizing the use of global variables, ensures that functions behave predictably and do not unintentionally alter other parts of the program. Finally, documenting functions with comments provides clarity for future reference, making it easier for collaborators or yourself to understand the function's role and how to use it. Custom and user-defined functions are fundamental to organizing and reusing code effectively in HCL. Understanding parameters, return values, and scoping is critical for writing efficient and reliable programs. By applying best practices such as keeping functions focused, using clear names, and avoiding side effects, you can create maintainable and scalable code. Practicing the creation and testing of functions for real-world applications will help solidify your skills and improve your ability to solve complex problems. As you continue to work with HCL, these concepts will become second nature, enabling you to build robust and well-structured programs. HCL stands for HashiCorp Configuration Language, and it is a declarative language specifically designed for infrastructure as code. This means that instead of writing procedural code to describe how to build infrastructure, you define what the infrastructure should look like, and the system figures out how to achieve it. HCL is known for its simplicity and readability, making it accessible even to those who are new to infrastructure automation. Its cross-platform compatibility ensures that the same configuration files can be used across different environments, whether on-premises or in the cloud. This language is widely adopted within HashiCorp's ecosystem, including tools like Terraform, which is used for provisioning infrastructure, Packer for creating machine images, and Vault for managing secrets. By using HCL, teams can create consistent, version-controlled infrastructure definitions that are easier to maintain and scale. Multi-cloud environments refer to the practice of using services from multiple cloud providers, such as Amazon Web Services, Microsoft Azure, and Google Cloud Platform. This approach offers several advantages, including redundancy, which ensures that if one cloud provider experiences an outage, services can still run on another. It also enables cost optimization, as organizations can choose the most cost-effective services from different providers. Another key benefit is avoiding vendor lock-in, which occurs when a company becomes overly dependent on a single provider's ecosystem. However, Multi-cloud environments also come with challenges. The complexity of managing multiple cloud platforms can increase operational overhead. Security becomes more intricate, as policies and controls must be consistently applied across different providers. Additionally, resource management across diverse platforms requires careful planning to ensure efficiency and compliance. In the context of multi-cloud environments, HCL plays a crucial role by enabling consistent infrastructure definitions across different cloud providers. This consistency is achieved by abstracting cloud-specific configurations, allowing teams to write modular and reusable code that can be applied to various environments. For example, a single HCL module might define a virtual machine configuration that works on AWS, Azure, or GCP with minimal adjustments. This abstraction reduces the need to rewrite infrastructure code for each cloud provider, saving time and reducing errors. Furthermore, HCL supports dynamic cloud resource provisioning and management, which means that infrastructure can be automatically scaled or adjusted based on real-time demands. This capability is essential for organizations that need to adapt quickly to changing workloads while maintaining control over their cloud resources. The key features of HCL that make it suitable for multi-cloud scenarios include its declarative syntax, modular design, and integration with cloud APIs. The declarative syntax allows users to specify the desired state of their infrastructure without worrying about the step-by-step process to achieve it. This approach simplifies complex configurations and makes them easier to understand and maintain. The modular design of HCL promotes reusability, as components like network configurations or security policies can be encapsulated into modules and shared across different cloud providers. Finally, HCL integrates seamlessly with cloud APIs through providers, which are plugins that enable HCL to interact with specific cloud services. For instance, the Oz provider allows HCL to manage EC2 instances, while the Azure provider handles virtual machines on Microsoft's platform. This integration ensures that HCL can leverage the full capabilities of each cloud provider while maintaining a unified configuration language. HCL is particularly useful in multi-cloud scenarios for several use cases. One common application is deploying applications across hybrid cloud environments, where some resources are hosted on premises and others in the cloud. HCL allows teams to define infrastructure in a way that bridges these environments, ensuring consistency and reducing complexity. Another use case involves automating cross-cloud resource provisioning, where HCL scripts can dynamically create and configure resources on multiple cloud platforms simultaneously. This automation is critical for organizations that need to scale rapidly or respond to changing business needs. Additionally, HCL helps manage policies and compliance across multiple clouds by enabling centralized configuration of security rules, access controls, and regulatory requirements. This ensures that all cloud environments adhere to the same standards, minimizing the risk of non-compliance. Despite its advantages, using HCL in multi-cloud environments presents several challenges. One of the primary challenges is managing the complexity of diverse cloud APIs, as each provider has its own set of tools, terminologies, and workflows. This can lead to inconsistencies in how infrastructure is defined and managed across different platforms. Ensuring consistent security policies across providers is another significant challenge, as security measures must be tailored to each cloud's unique features while maintaining a unified approach. Finally, versioning and dependency management in multi-cloud workflows can become complicated, as different environments may require different versions of HCL modules or providers. These challenges require careful planning, robust testing, and continuous monitoring to ensure that the infrastructure remains stable and secure across all cloud platforms. To effectively use HCL in multi-cloud environments, several best practices should be followed. First, leveraging modular HCL code allows organizations to create cloud-agnostic configurations that can be reused across different providers. This reduces duplication and ensures consistency. Second, Terraform workspaces can be used to manage environment-specific setups, such as development, testing, and production, without duplicating code. This approach helps maintain separate configurations for different stages of the development lifecycle. Third, implementing strict access controls and secrets management is essential for securing multi-cloud infrastructure. Tools like HashiCorp Vault can be integrated with HCL to securely store and retrieve sensitive information, such as API keys and passwords. By following these practices, teams can minimize risks, improve efficiency, and maintain control over their multi-cloud environments. In conclusion, HCL simplifies multi-cloud management by providing a declarative, reusable, and consistent way to define infrastructure across different cloud providers. Its ability to abstract cloud-specific details and integrate with cloud APIs makes it a powerful tool for organizations navigating the complexities of multi-cloud environments. However, success with HCL requires careful planning to address challenges such as API complexity, security policies, and dependency management. As more organizations adopt multi-cloud strategies to achieve scalability, cost efficiency, and resilience, HCL plays a vital role in enabling these goals. By following best practices and leveraging the full potential of HCL, teams can build secure, efficient, and future-proof multi-cloud infrastructures. Resource dependencies in the HCL programming language are fundamental to how components interact within workflows. These dependencies define the relationships between different resources, ensuring that each component is properly coordinated to achieve the desired outcome. Proper management of these dependencies is critical because it prevents conflicts that could arise from overlapping or conflicting operations, ensuring that workflows execute efficiently. HCL provides robust tools for both dynamic and static dependency resolution, allowing developers to handle complex scenarios where dependencies may change at runtime or be determined at configuration time. By leveraging these tools, teams can create more reliable and scalable systems. Advanced dependency scenarios in HCL often involve nested resource dependencies, where components are organized in complex hierarchies that require layered management. For example, a single resource might depend on multiple other resources, which in turn depend on additional components, creating a multi-level structure. Conditional dependencies add another layer of complexity, as they are triggered by runtime variables or logical conditions, enabling workflows to adapt dynamically to changing environments. Cross-environment dependencies further challenge developers by requiring the management of resources across different stages, such as development, testing, and production. These scenarios demand careful planning and configuration to ensure consistency and avoid disruptions. Dynamic dependency resolution in HCL is a powerful feature that allows dependencies to be defined using runtime expressions. This means that the relationships between resources can be determined at execution time rather than being hard-coded. The depends-in keyword in HCL supports this by enabling dependencies to be tied to variables or expressions that evaluate during runtime. Additionally, HCL S for loops can automate the mapping of dependencies, particularly useful when dealing with multiple instances of similar resources. For instance, a cloud deployment might dynamically link resources based on input variables, such as region or instance count, ensuring that dependencies are automatically adjusted to match the current configuration. Resource graph optimization in HCL involves visualizing dependencies to gain a clear understanding of how components interact. HCL's graphing tools provide a visual representation of these relationships, making it easier to identify potential issues such as circular dependencies, where two or more resources depend on each other in a loop. Resolving these circular dependencies is essential to prevent infinite loops or failed executions. Furthermore, optimization techniques can rearrange the execution order of resources to maximize parallelization, reducing overall runtime and improving performance. By analyzing and refining the resource graph, teams can ensure that workflows are both efficient and reliable. Conflict resolution strategies in HCL are designed to handle situations where dependencies might clash or where resources have incompatible configurations. One approach is to prioritize dependencies using a priority attribute, which dictates the order in which resources are processed. This is particularly useful when multiple dependencies could affect the same resource. Version mismatches can be addressed by specifying explicit version constraints, ensuring that resources use compatible versions of shared components. When conflicts persist, HCL provides override mechanisms that allow manual intervention, giving teams the flexibility to resolve issues without relying solely on automated rules. Best practices for advanced dependency management in HCL emphasize modularity, documentation, and thorough testing. Modularizing dependencies involves breaking down complex systems into smaller, self-contained modules, making it easier to manage and update individual components without disrupting the entire system. Documenting dependency chains is essential for clarity, especially in large projects where multiple teams may be involved. This documentation also aids in auditing and troubleshooting. Testing scenarios with edge cases, such as missing resources or unexpected input values, ensures that workflows remain resilient under various conditions. These practices collectively enhance maintainability and reduce the risk of errors. Real-world use cases for HCL's dependency management highlight its versatility in different scenarios. For example, deploying microservices often requires interdependent APIs, where each service must be configured to wait for its dependencies to be ready before starting. In infrastructure as code workflows, managing dependencies during continuous integration and continuous delivery pipelines ensures that changes are applied in the correct order, avoiding conflicts. Multi-team projects may face conflicts when different teams modify shared resources, and HCL's tools help resolve these by enforcing constraints and prioritizing changes. These examples demonstrate how effective dependency management is critical for successful deployment and collaboration. Mastering advanced resource dependency management in HCL is essential for building robust and scalable workflows. By understanding dynamic resolution techniques, teams can create flexible systems that adapt to changing conditions. Optimizing resource graphs ensures that execution is efficient and avoids bottlenecks. Conflict resolution strategies provide the tools needed to handle inevitable clashes in complex environments. Applying these best practices not only improves the reliability of HCL configurations, but also enables teams to manage increasingly complex systems with confidence and precision. HCL's security framework is designed to protect data and systems through a layered approach that combines technology, processes, and people. In programming, security policies are essential because they establish guidelines to prevent unauthorized access, data breaches, and other vulnerabilities that could compromise sensitive information. Compliance plays a critical role in maintaining data integrity by ensuring that all operations adhere to legal and industry-specific standards. This not only safeguards the organization, but also builds trust with stakeholders and customers. Data encryption is a cornerstone of HCL's security strategy, ensuring that information remains secure whether it is stored or transmitted. This involves using robust encryption algorithms to transform data into unreadable formats that can only be decrypted with the correct keys. Role-based access control, or RBAC, is another vital component, as it restricts system access based on user roles, reducing the risk of internal threats. Regular vulnerability assessments and patch management are equally important, as they help identify and address weaknesses in software and infrastructure before they can be exploited by malicious actors. HCL compliance frameworks are built to align with global regulations, such as the General Data Protection Regulation, which mandates strict data protection practices for European Union residents, and the Health Insurance Portability and Accountability Act, which governs healthcare data in the United States. The International Organization for Standardization sets benchmarks for quality and security management systems, ensuring consistency across industries. Audit trails are essential for tracking user activities and system changes, providing a clear record for investigations or compliance checks. Data localization requirements further complicate global deployments by necessitating that data be stored and processed within specific geographic boundaries to meet legal obligations, preventing SQL injection and cross-site scripting attacks requires developers to implement rigorous input validation and output encoding practices. These vulnerabilities often arise from improper handling of user inputs, so HCL applications must sanitize all data before processing. Secure coding practices include following the principles of the secure development lifecycle, which integrates security at every stage of software development. Tools like static code analysis are used to automatically detect potential security flaws in the code base, allowing teams to address issues early in the development cycle and reducing the risk of exploitation. Regular security training ensures that developers stay updated on the latest threats and best practices, fostering a culture of vigilance. Secure configuration of HCL environments involves setting up systems with minimal attack surfaces, such as disabling unnecessary services and applying the principle of least privilege. incident response planning and reporting protocols are critical for minimizing damage during a security breach, as they outline clear steps for containment, investigation, and communication with stakeholders. These measures help organizations respond swiftly and effectively to incidents while learning from them to prevent future occurrences. A case study on securing a financial HCL application might highlight how encryption, access controls, and real-time monitoring were used to prevent unauthorized transactions and data leaks. Lessons from compliance audits often reveal gaps in documentation or processes, emphasizing the need for continuous improvement. Success stories demonstrate how HCL implementations have met regulatory demands through proactive measures, such as automated compliance checks and collaboration with legal teams to stay ahead of evolving requirements. These examples underscore the importance of aligning security strategies with both technical and regulatory priorities. In summary, HCL security relies on a combination of well-defined policies, compliance with global standards, and proactive threat mitigation. Developers must prioritize security at every stage of the software lifecycle, from design to deployment. By committing to continuous learning and adherence to best practices, teams can build resilient systems that protect data and maintain user trust. Let this presentation serve as a reminder that security is not a one-time effort, but an ongoing commitment to excellence and innovation. Automation transforms how we approach software development by reducing manual effort and increasing reliability. It involves creating systems that perform tasks with minimal human intervention, which is crucial in today's fast-paced environments. HCL serves as a powerful tool for scripting and automation, offering a structured way to define and execute processes. Whether you're managing infrastructure, testing applications, or deploying code, HCL helps streamline these activities. The benefits of using HCL include improved efficiency, as repetitive tasks are handled automatically. Consistency, since scripts follow predefined rules. And scalability, allowing you to expand automation across larger systems without proportional increases in effort. At the heart of HCL scripting are variables, loops, and conditionals, which form the building blocks of logic. Variables store data that can be reused throughout a script. Loops enable repetitive actions, and conditionals allow decisions based on specific criteria. Functions in HCL let you encapsulate reusable code, making scripts modular and easier to maintain. For instance, a function might handle file input and output, which can be called multiple times without rewriting the same code. Integration with HCL tools like HCL OneTest and HCL Launch extends these capabilities, enabling automation of testing workflows and deployment pipelines. These tools work seamlessly with HCL scripts to create end-to-end solutions. To begin writing HCL scripts, you first need to set up the environment. This typically involves installing the HCL runtime and configuring the necessary tools. Once ready, the basic syntax of an HCL script starts with the keyword script, followed by a block of code enclosed in curly brackets. For example, script defines the main execution block. Another key construct is define, which is used to create reusable components. Let's walk through an example. A script that automates file manipulation. Suppose you want to rename all files in a directory with a specific extension. The script would use loops to iterate through files, conditionals to check extensions, and functions to perform the renaming. This demonstrates how HCL can simplify complex tasks with clear, structured code. Adopting best practices in HCL scripting ensures your code remains manageable and effective over time. Modular design is essential, breaking scripts into smaller, self-contained functions makes them easier to debug and update. For instance, a script handling user authentication might have separate functions for input validation, database queries, and error reporting. Error handling is another critical aspect. By using try-catch blocks or logging mechanisms, you can track issues and prevent scripts from failing silently. Version control systems like Git help manage changes, while thorough documentation ensures others can understand and build upon your work. These practices turn raw scripts into robust, collaborative solutions. Debugging and testing HCL scripts is vital to ensure they function as intended. Tools like the HCL debugger allow you to step through code, inspect variables, and identify logical errors. Unit testing involves verifying individual components, such as a function that calculates a value, while integration testing checks how these components work together in a larger workflow. Common pitfalls include syntax errors, which can be caught early with linters, or logical errors that produce unexpected results. Troubleshooting tips include adding detailed logs to trace execution flow and using version control to revert to stable states. By prioritizing testing, you minimize risks and build reliable automation. HCL's integration with tools like HCL One Test and HCL Launch expands its utility in real-world scenarios. With HCL One Test, you can automate testing processes, such as validating application behavior under different conditions. For example, a script might simulate user interactions to check for bugs. In HCL Launch, scripts can manage deployment pipelines, automating steps like code compilation, testing, and deployment to production. Additionally, HCL scripts can interact with external systems via APIs, enabling tasks like fetching data from cloud services or updating third-party tools. These integrations make HCL a versatile choice for connecting diverse systems and workflows. Real-world applications of HCL scripting are vast and impactful. Consider a case study where HCL automates CI/CD pipelines, ensuring code changes are tested and deployed efficiently. A script might trigger a build, run tests, and deploy to a staging environment, all without manual intervention. Data processing scripts can extract, transform, and load data from multiple sources, generating reports for stakeholders. In DevOps, HCL scripts automate infrastructure provisioning, while system administrators use them to manage servers, monitor performance, and enforce policies. These examples highlight how HCL turns complex, repetitive tasks into automated, scalable solutions, empowering teams to focus on innovation. To summarize, HCL scripting is a cornerstone of modern automation, offering tools to streamline workflows and enhance productivity. Key principles include writing modular, well-documented code, integrating with HCL tools, and prioritizing testing and debugging. Practice is essential. Experimenting with small scripts and gradually tackling more complex tasks builds proficiency. As you explore advanced techniques, such as integrating with APIs or optimizing performance, you'll unlock new possibilities. Remember, the goal of automation is not just to save time, but to create create reliable, scalable systems. Keep learning, stay curious, and apply these concepts to real-world challenges. Welcome to session 36, focused on advanced module versioning and updates within the HCL programming language. This session is designed to help you gain a deep understanding of how to manage version control, automate updates, and ensure compatibility across different modules. By the end of this session, you will be equipped with strategies to navigate the complexities of module versioning, implement automation for updates, and effectively resolve conflicts that may arise during the process. The key objectives include exploring versioning strategies, learning how to automate updates, and developing skills to address conflicts. Let's begin by discussing why module versioning is essential in HCL. Module versioning plays a critical role in maintaining consistency across environments and teams. When multiple teams work on different parts of a project, having a standardized versioning system ensures that everyone is on the same page. This consistency prevents breaking changes in dependent modules, which can lead to unexpected errors and downtime. For example, if a module is updated without proper versioning, other modules relying on it might fail to function correctly. Versioning also facilitates rollback and debugging in production systems. If a new version introduces a critical issue, you can quickly revert to a previous stable version. Additionally, versioning supports collaborative development by establishing clear release cycles, allowing teams to plan and coordinate their work effectively. In HCL, semantic versioning is a widely adopted approach. This method uses a 3-part version number in the format major.minor.patch. The major version is incremented when there are incompatible changes, such as breaking existing functionality. The minor version is used for adding new features that do not break existing functionality, while the patch version is reserved for bug fixes and minor updates. For instance, a version like v123 indicates a stable release with bug fixes, whereas v200 signifies a major update with potential breaking changes. By adhering to this structure, developers can clearly communicate the nature of changes in a module, making it easier for others to understand and manage dependencies. Effective version control strategies are essential for managing HCL modules. One common practice is to use version tags, such as v100, to mark stable releases. These tags act as milestones, making it easier to track and reference specific versions of a module. Branching strategies also play a key role, with separate branches for development, testing, and production. This allows teams to work on new features or fixes without disrupting the stable code base. Git-based workflows further enhance version control by providing tools to track changes and collaborate efficiently. Additionally, version pinning is crucial to avoid unintended upgrades in dependencies. By specifying exact versions, you ensure that modules use compatible versions of their dependencies, reducing the risk of conflicts. Automated update mechanisms are vital for streamlining the process of applying updates to HCL modules. Integrating continuous integration and continuous deployment pipelines allows for automatic testing of new versions, ensuring they meet quality standards before deployment. Tools for dependency scanning can identify outdated or vulnerable modules, providing alerts when updates are needed. Scripted workflows further enhance automation by applying updates across multiple modules consistently. For example, HCL-specific tools can validate versions and ensure compatibility during deployment. These mechanisms save time, reduce human error, and allow teams to focus on more complex tasks while maintaining up-to-date modules. Dependency management is a critical aspect of module development in HCL. When defining dependencies, it's important to use version ranges to specify acceptable versions. For instance, a range like greater than or equal to 120 and less than 200 allows for flexibility while avoiding major changes. Lock files are another essential tool, as they enforce exact versions for reproducibility. This ensures that every instance of the module uses the same dependencies, preventing discrepancies across environments. Monitoring external module updates is also crucial for addressing security vulnerabilities and performance improvements. By keeping dependencies up to date, teams can maintain the reliability and efficiency of their HCL projects. Conflict resolution is a key skill when managing module versions in HCL. Version conflicts often arise when dependencies require different versions of the same module. Identifying these conflicts using dependency graphs helps visualize the relationships between modules and their dependencies. Prioritizing compatible versions during upgrades ensures that the system remains stable. Strategies for backward compatibility, such as deprecation warnings, allow teams to transition smoothly to newer versions. In critical situations, manual intervention may be necessary to resolve conflicts in production environments. By proactively addressing conflicts, teams can minimize disruptions and maintain the integrity of their systems. Best practices for updates are essential for maintaining the reliability of HCL modules. Testing updates in isolated environments before deployment ensures that changes do not introduce issues in production. Documenting changes in release notes provides transparency, helping teams understand what has changed and why. Using versioning to track module evolution over time allows for better planning and accountability. Regularly auditing dependencies is also important to identify outdated or vulnerable modules. These practices, when combined, create a robust workflow that supports continuous improvement while minimizing risks. Let's examine a real-world case study involving the update of a legacy HCL module with breaking changes. In this scenario, the team faced challenges due to outdated dependencies and incompatible updates. The process began with version tagging to mark the current state of the module. Testing was conducted in isolated environments to ensure stability. Rollback plans were established to quickly revert to previous versions if issues arose. Clear communication with stakeholders ensured everyone was aware of the changes and their impact. The outcome included minimized downtime and improved collaboration among teams. Key lessons learned emphasized the importance of versioning, proactive planning, and effective communication in managing complex updates. Mastering module versioning is essential for ensuring stability and scalability in HCL projects. By implementing automation and clear strategies, teams can reduce the risks associated with updates. Continuous learning and adherence to best practices are critical for long-term success. As we conclude this session, I encourage you to apply the concepts discussed to your projects. In our next session, we will explore advanced debugging techniques in HCL, building on the foundation laid here. Thank you for your attention, and I look forward to seeing how you implement these strategies in your work. Good afternoon, everyone. Today, we will explore how the HCL programming language is applied in real-world scenarios. HCL, or HashiCorp Configuration Language, is a powerful tool designed to manage infrastructure as code, enabling developers and system administrators to automate and streamline complex processes. By examining case studies, we can better understand how HCL addresses practical challenges and enhances efficiency. Our primary objective is to analyze real-world problems and identify how HCL provides effective solutions. Whether it's optimizing healthcare systems or managing e-commerce platforms, HCL's flexibility and robustness make it a valuable asset across industries. Let's dive into specific examples to see how these concepts come to life. Let's take a closer look at a case study involving HCL in a hospital data management system. Hospitals generate vast amounts of data, from patient records to inventory tracking, requiring systems that can scale efficiently. HCL's modular architecture allows for seamless integration with existing infrastructure, ensuring scalability. Real-time data processing is another critical feature, enabling healthcare providers to access up-to-date information quickly. For instance, automated systems can track patient admissions, allocate resources, and even predict staffing needs based on historical data. The results of implementing HCL in such environments have been remarkable, with one hospital reporting a 30% reduction in administrative overhead. This not only saves time, but also reduces costs and minimizes human error, allowing staff to focus on patient care. Next, consider the application of HCL in e-commerce platform development, particularly in dynamic pricing algorithms. E-commerce businesses rely on predictive analytics to adjust prices in real time based on demand, competition, and user behavior. HCL facilitates this by providing a framework for integrating machine learning models that analyze vast data sets. For example, when a sale event begins, the system can automatically adjust prices to maximize revenue while maintaining customer satisfaction. However, this approach comes with challenges. Handling high traffic during peak times requires robust load balancing and efficient resource allocation. HCL's ability to manage infrastructure as code ensures that systems can scale dynamically, preventing downtime and ensuring a smooth user experience. This adaptability is crucial for maintaining a competitive edge in the fast-paced e-commerce landscape. Another compelling use case is HCL's role in financial services automation, specifically in fraud detection systems. Financial institutions process millions of transactions daily, making it essential to detect suspicious activities promptly. HCL integrates with machine learning technologies to analyze transaction patterns and flag anomalies in real time. For example, by leveraging historical data, these systems can identify unusual spending habits or unauthorized access attempts. This integration significantly reduces the time required for transaction verification, with one implementation achieving a 40% faster verification process. The result is enhanced security and reduced financial losses. HCL's ability to automate these processes not only improves accuracy, but also allows teams to focus on more strategic tasks, ultimately strengthening the integrity of financial systems. Now, let's explore HCL's application in IoT device management, particularly in monitoring smart infrastructure. As cities become more connected, the need for real-time monitoring of devices such as sensors, cameras, and environmental controls grows. HCL enables seamless communication between embedded systems and cloud platforms, ensuring data is processed and stored efficiently. For instance, in urban environments, HCL can manage networks of smart streetlights that adjust brightness based on pedestrian activity or monitor water usage in real time. This integration leads to improved maintenance efficiency, as issues can be identified and resolved before they escalate. By reducing manual intervention, HCL helps cities operate more sustainably and cost-effectively, demonstrating its value in large-scale, complex systems. Despite its advantages, deploying HCL in real-world scenarios presents challenges. Common issues include ensuring scalability to handle growing data demands, maintaining robust security protocols, and optimizing performance under heavy workloads. HCL's modular design addresses these concerns by allowing developers to build and test components independently, reducing the risk of system-wide failures. For example, when scaling a healthcare data management system, modular components can be upgraded without disrupting existing operations. practices for deployment include rigorous testing, continuous monitoring, and implementing security measures such as encryption and access controls. By following these strategies, organizations can maximize HCL's potential while minimizing risks, ensuring reliable and efficient systems. In summary, we've examined how HCL is applied across diverse industries, from healthcare and e-commerce to finance. And IoT Each Case Study highlights HCL's versatility in solving complex problems through automation, scalability, and real-time processing. The success of these implementations underscores HCL's role as a critical tool for modern infrastructure management. As you continue your learning journey, I encourage you to apply these concepts in your own projects. Whether you're optimizing a system or developing a new solution, HCL offers the flexibility and power to turn theoretical knowledge into practical results. Let's continue exploring the possibilities and harnessing HCL's full potential in the ever-evolving tech landscape. Advanced debugging is a cornerstone skill for any developer working with the HCL programming language. It goes beyond simple error correction. It involves a deep understanding of how code interacts with itself and the environment. Imagine you're troubleshooting a complex application where a bug only appears under specific conditions. Without systematic problem solving, you might waste hours chasing red herrings. By approaching debugging methodically, breaking down the problem into smaller parts, testing hypotheses, and verifying results, you can efficiently isolate and resolve issues. This process not only fixes immediate problems, but also enhances the overall reliability and performance of your code, ensuring it runs smoothly even under stress or unexpected scenarios. Breakpoints are your primary tool for pausing code execution at critical points to inspect its behavior. For example, if you suspect a function is causing an issue, setting a breakpoint there allows you to step through each line and observe variable states. Conditional breakpoints take this further by triggering only when specific criteria are met, such as a variable exceeding a threshold or a particular input being processed. This is invaluable in scenarios with loops or event-driven systems where you want to focus on rare or specific conditions. Data breakpoints, on the other hand, monitor changes to variables or memory locations, helping you track when and why a value is altered. This is especially useful for diagnosing race conditions or unexpected state changes in multi-threaded applications. When debugging, inspecting variables and memory is essential to understand what your code is actually doing. You can use the debugger to check the current value of a variable, its data type, and even its memory address. This helps identify issues like type mismatches or uninitialized variables. Exploring stack and heap memory structures reveals how data is allocated and managed. For instance, a stack overflow might indicate a deep recursion issue, while a memory leak could point to unmanaged resources. Tracking variable scope and lifetime during runtime ensures you understand when and where variables are accessible, preventing issues like accessing deleted data or unintended side effects from global variables. Stack traces are like a roadmap of function calls leading up to an error. They show the sequence of function invocations, helping you pinpoint where a problem originated. For example, if an exception is thrown, the stack trace reveals the exact line and function where it occurred, even if it was triggered from a nested call. Call hierarchies expand on this by visualizing the relationships between functions, making it easier to trace the flow of execution. This is crucial for diagnosing recursion or infinite loops, where a function might call itself repeatedly without a proper exit condition. By analyzing the stack, you can identify these patterns and adjust the logic to prevent crashes or performance degradation. Logging and tracing are powerful techniques for monitoring code behavior without interrupting execution. Detailed logs capture events, variable states, and error messages, providing a historical record of what happened. Trace statements, often used in conjunction with logs, help track the flow of execution through different parts of the code. For instance, you might log the entry and exit of a function to see how often it's called or what parameters it receives. Combining logging with a debugger creates a hybrid approach. Logs give a high-level overview, while the debugger allows you to dive into specific details. This dual strategy is especially useful for diagnosing intermittent issues that are hard to reproduce. HCL offers specialized debugging tools and plugins designed to streamline the process. These tools might include syntax checkers, memory analyzers, or integrated performance profilers. Leveraging your IDE's features, such as watch windows, allows you to monitor variables in real time as the code runs. Step through execution lets you navigate line by line, observing how the program state evolves. Integrating with external profilers extends this capability, enabling you to analyze performance bottlenecks such as slow functions or excessive memory usage. By combining these tools, you can address both functional and performance issues, ensuring your HCL applications are robust and efficient. In summary, mastering advanced debugging techniques requires a blend of breakpoints, variable inspections, and logging. These methods form the foundation of effective troubleshooting. Systematic workflows, such as isolating problems, testing hypotheses, and verifying solutions, are critical for consistent results. However, no amount of theory replaces hands-on practice. Real-world scenarios, like debugging a production bug or optimizing a slow-running script, provide invaluable experience. By applying these techniques regularly, you'll not only resolve issues faster, but also develop a deeper understanding of how HCL applications behave, leading to more reliable and efficient code. Production-ready HCL is a term that encapsulates code that is not only functional, but also designed to scale, protect data, and remain easy to maintain over time. In enterprise environments, where systems often handle vast amounts of data and critical operations, the importance of robust HCL cannot be overstated. It ensures that infrastructure and configurations are reliable, adaptable, and resilient to changes. The objectives of this session are to explore best practices that guide developers in writing clean and efficient HCL, implement effective error handling to prevent failures, optimize performance to meet demanding workloads, and enforce security measures to safeguard sensitive information. By focusing on these areas, teams can create HCL code that stands the test of time and supports business goals. Modularizing code in HCL is a foundational practice that allows developers to break down complex systems into manageable, reusable components. By creating modules and functions, teams can reduce redundancy, improve readability, and streamline updates. Consistent naming conventions and structured code organization are equally vital, as they ensure clarity for collaborators and future maintainers. Documenting code through comments and external resources is another critical step, as it provides context and reduces the learning curve for new team members. HCL also offers built-in validation and type-checking features that help catch errors early, ensuring that configurations adhere to expected formats and constraints. Together, these practices foster a culture of efficiency and collaboration. Exception handling in HCL is essential for building resilient systems that can recover from unexpected issues. Using try-catch blocks, developers can isolate potential errors and define fallback mechanisms, preventing cascading failures. Logging and debugging tools provide visibility into the execution flow, making it easier to trace issues and resolve them quickly. Validating inputs and outputs at key stages of a script helps prevent invalid data from causing downstream problems, while testing edge cases ensures the code can handle unusual scenarios without crashing. These strategies not only improve reliability, but also make troubleshooting more systematic and less time-consuming. Performance optimization in HCL involves strategic decisions that minimize resource waste and maximize efficiency. Redundant resource creation can lead to unnecessary costs and delays, so reusing modules and templates is a best practice. Optimizing data structures, such as using maps for fast lookups or lists for sequential access, ensures that operations run smoothly even with large datasets. Parallelism can be leveraged in scenarios where tasks are independent, allowing multiple operations to execute simultaneously and reducing overall processing time. Finally, monitoring and profiling HCL scripts helps identify bottlenecks, enabling targeted improvements that enhance scalability and responsiveness. Security in HCL requires vigilance to protect sensitive information and prevent vulnerabilities. Hard-coding secrets like passwords or API keys is a major risk, as it exposes them to potential leaks. Instead, HCL provides secret management tools and encryption features to handle such data securely. Validating user inputs is another critical step, as it prevents injection attacks that could compromise the integrity of configurations. Regular code audits ensure that security practices remain up to date with evolving threats, and integrating security checks into the development lifecycle reduces the likelihood of breaches. These measures create a safer environment for deploying and managing infrastructure, testing and validation are cornerstones of producing reliable HCL code. Writing unit tests for individual modules ensures that each component functions as intended, while linters and static analysis tools catch syntax errors and style inconsistencies. Integration tests simulate real-world scenarios, verifying that different parts of the system work together seamlessly. Automating these tests through CI/CD pipelines ensures that changes are validated continuously, reducing the risk of introducing errors. By combining these strategies, teams can maintain high code quality and confidence in their deployments. Real-world applications of HCL demonstrate its versatility and power. For example, deploying scalable infrastructure involves using modules to replicate configurations across environments, ensuring consistency and reducing manual effort. Managing secrets in multi-environment setups requires leveraging HCL's encryption and vault integration to keep credentials secure. Automating compliance checks allows organizations to enforce policies dynamically, ensuring adherence to regulations. Finally, optimizing performance for high-traffic systems involves tuning data structures and using parallel processing to handle large workloads efficiently. These examples highlight how HCL can address complex challenges in practical settings. In conclusion, creating production-ready HCL demands a commitment to discipline, thorough testing, and proactive security measures. Prioritizing modularity, performance, and maintainability ensures that code remains adaptable and efficient as requirements evolve. Continuous learning is essential, as best practices and tools in the HCL ecosystem are constantly advancing. By applying the concepts discussed in this session, developers can build robust, secure, and scalable solutions that meet the demands of modern enterprises. The key is to remain diligent, adaptable, and focused on long-term quality. And just like that, our dreamy coding adventure has come to an end. I hope the gentle ebb and flow of the tutorial, combined with the tranquil melodies, have left you feeling both informed and at ease. Whether you managed to catch every line of code or drifted off into a peaceful slumber, remember that the world of HCL will always be here waiting for you. Keep your code clean, your mind open, and your spirit relaxed. forget to subscribe to Code Snooze so you never miss out on another soothing coding journey. Hit that like button if this video brought you a moment of calm and learning, and share it with fellow coders or anyone in need of a serene study session. Thank you for joining me in this cozy corner of the internet. Until next time, may your code run smoothly and your dreams be filled with brilliant algorithms. Sweet dreams, sleepy coders.